All right, welcome, everybody online. Can you hear me? Sorry, it's a little chaotic right now, getting up online.
Yeah, we can hear.
Great, thank you so much. Welcome. This is Optimize Week 9. A little mood lighting there. All right. All right, we're starting to get a little bit closer to the end line here. So today, what we're going to go over problems with existing homework, and then we're going to go into how do you optimize from a profiling standpoint, understand how to profile your tool. Remember, I had everybody get the really kind of fancy, expensive enterprise edition. That has a couple extra features in it, really nice that allow us to do profiling. But first, I want to talk about the homework, right? So let's talk about any problems with homework. I guess we're on PA 8 and Basics 8, right? So how it works is I'm going to give you a list, and you don't know the size of it. But there are going to be certain parameters. The parameters are there's always an even number of columns, and there's 1 to n rows. So in this case here, here's how this works. Right, and then this one goes in, this goes out, this goes in, this goes out, right? And everything else is nulls. Or I might give you something like this. Right, and we any dimensions, and your job is just to delete 1. Right, so it's not no matter what I give you, I'm going to give you a perfectly brand new list and just delete 1, right? And some strategies here, right? So I'll kind of give you the approach I went with, but you can kind of go through this now that you get your hands dirty. Is at some point, remember the goal of this was to create a data structure that's not necessarily in books yet, and to torment you with linked lists and solid programming skills, right? So let's say here's our grid, right? And the goal is to remove, let's say, this guy here, this node, right? I'll put a big X in here, right? The pointers kind of do this, we'll do in blue. Right, and then they go out, they go out. Right, they go in. So if the goal is to remove this guy here, right? The approach I went with is find my 4 neighbors every single time. So I'll find, the north one, the east, the south, and the west, right? So I will find these yellows. So I created a helper function that says, hey, I want you to remove this node. Go find the 4 neighbors. And it finds the 4 neighbors. Now, here's the catch. I have another function that says, given 4 neighbors, remove the node, right? So all I do is I delete this, right? Now I have to fix the pointers. So remember, I have in my hand north, south, east, west, right? So I know like, oh, the east comes out this way and it's going to keep going until it hits west. Nothing comes out of south and nothing comes out of north. Done. Right? And there's no more thinking about it than that. All right, so now let's do a different one. All right, so let's say this guy here, right? So I turn around and go, okay, I know the drill. Right, so I have all the yellows. So I have one function that gets the yellows, and I just delete this. Boom. Now I look at everything here. The east comes out, right? So this one continues across. Right, the south comes out, so the south is continues until it hits the north. The north comes out and it continues to hit the south. Okay. So I wrote 2 functions. One is find the 4 neighbors. Sometimes they're null. Sometimes they're null. And then I say, given my 4 nodes, remove the node in the center. And also my complexity goes down to nothing. Right?
I definitely overthought that and did way too much.
A lot.
Like, I mean,
Now, every scenario here, no matter what, if you kind of look at it from a, I gave you a 3x4.
which was in the test.
Right in the test, right?
Yeah, the 3x4, yeah.
And this 3x4 is every edge condition that can possibly be existing, right? So if we had a grid, no matter how complicated the grid is, I can place this 3x4 somewhere on it, and there's all the edge conditions.
Right.
So even if the grid's really, really, really large, assuming I did this all aligned correctly.
Yeah.
We don't have a 3x4 in the test, just in the right.
Just in the write-up this way, I showed you every edge condition. All these edge conditions, no matter where we put this, are covered in this one 3x4.
Right.
And the reason I did that is I wanted you to have no like pissing match later saying, mine's right, yours wrong. And like, well, here's all the edge conditions. So you kind of see it on paper.
So are you gonna test our code with the new tests then?
Okay, so what you got now is
It's a 2x2,
the homework.
isn't it?
The homework is, I wanted you just to practice. Because the question is like, I didn't know you were gonna delete the node. I didn't know how to delete it. There's gonna be all these like arguments after the fact. So I'm like, fine, here's a 2x2. To pass this 2x2 test, you have to find the neighbors and then delete the correctly. Now you understand the pattern. I'm gonna give you something with different sizes and say, delete number 5,3. And you delete it. It will exist. I'm not gonna give you a size that doesn't exist in the grid. So if I give you a 16 by 16 grid, I'm not gonna say remove number 22, 33.
All right.
It will be 0 through 15.
You're always starting us with like a pristine.
I'm gonna give you a perfectly good thing, and you're just gonna delete one node,
All right, then, okay.
right? And what will happen is sometimes you delete a node that's not walkable. Like, if I delete this node, I can never walk to this node. It's okay, I just actually delete the node. I didn't ask you, can you walk to the other nodes? Is it orphaned? So if we look at the unit, the scenario,
Yeah, they break the flow.
some of those just aren't possible. Here's the stuff. No, I have it somewhere. Oh, of course, I didn't. Stooge. I just didn't update it on my side. All right. So some poor student, I know that they have it. Okay. It's Adobe. All right, so what?
You have to sign in to use Adobe. That's
Oh,
why.
really?
it
All right, well then
this.
I'll just use this lame thing. You get to sign in, use Adobe, that's kind of sad. All right, so the assumption is gonna be that you were given a perfectly pristine, the bottom here, you give pristine grid, you just have to delete one node. You don't know the dimensions, but they'll be null terminated in the correct way. Always even number of columns, unlimited restriction on rows, and you're just going to delete. That's it. But you'll see here in some of the patterns. Let's see if I get one here. Like here, you'll never be able to get to this guy, but that's a correct deletion. So what I do is I generate the maze. I have a library that has all the pointers to it. Then I check each of your nodes. So it's pretty intensive on my unit test. So I drop in this little library and a magic happens.
All right, so we wouldn't be given a list like this though, it'd be full.
You just have that function and I feed the function. And
Oh, so it's just to make sure that that node still exists on your end.
I'm gonna check here. So in this case here, what my unit test does is, and if you look at the thing here, I first start off with verify the grid. I verify every node, every link of the whole stinking grid, right? Which is time consuming. Then I say delete a node. Delete this node. I go every single node and check everybody's pointer.
Right, okay.
All 4 pointers of each node of every single thing on the grid. Right? No, that's one test.
Okay, I see.
So then I'm going to give you a brand new grid and say delete 3, 2.
So
Then I test every single thing again. Then I'm like brand new grid, delete 5, 5.
so every test is always should be deleting something. You should never
You'll be
test that's not.
deleting one thing. And that's what the unit test was supposedly, the test I gave you is to train you that you have to delete something.
All right, that's okay. I
If
was
you don't
confused. I
delete
thought you
something,
said
you won't
that.
pass the test. So like right now, you're 2 by 2. You're deleting something, right?
Okay, because I was confused because that one picture it looked like you were deleting into her node. I'm like, but that's not even, okay. That makes more sense.
So here. Cool. All right, there's 8. So on this one here. Let me make sure I'm not. Good, they're all ones. All right. Because I didn't upload it correctly. All right, so here on this one. I put in a unit test. I'm going to replace this library and these unit tests when I grade yours with something, right? And I'm just going to run off the grade and kind of look at it, right? But what I'm doing in the unit test is going to be indicative. I'm going to, in this case here, this is a 2 by 2. I'm going to check all the nodes. You're going to remove 1, so it's called your code. It'll remove 1. And then I'm going to check all the nodes again. And then I got to make sure that you aren't leaking memory. You did delete that one.
Right, okay.
You know what I mean? So if you delete the one, then this should pass. So if you can get these first 2 by 2s working, you at least know kind of what to expect. Now the next question is your function right? is this function correct for all scenarios?
Yeah, what I've realized is the only thing that this test can't do is verify that you're pointing through vertically and like the
Yeah,
north
it
south.
does. It does.
But if it's a 2x2, you're not gonna really have a point through.
No, not the test you're given doesn't test everything, but he has.
Yeah, that's what I meant, the test, so it's kind of
So here's a
hard to
2
know
by
if
2,
my
right?
point through is gonna work there.
Here's a 2 by 2. Right, there, let me do the 2 by 2. So here's a node, here's a node, right? Everything else is nulls, right?
Yeah.
So, oh, I see what you're saying. I just didn't give a big enough unit test. So if you deleted this one, that's what you should get.
Yeah, but I mean, like, if you have a 3x3 and say you delete the middle one and, or wait, pointing, I'm trying to think odd even node, it's.
3 by 3 is not allowed.
No.
Yeah,
I mean, 4 by,
because,
like a 3x4, just something where there's like a not, where there's bigger than 2 rows, because that's where the north-south matters.
What's your question though? I don't.
Yeah,
Well, the unit test, so like,
it's gonna test everything.
so like,
Just trust me, if you did it wrong, I will find your mistake. and then
no, I mean,
Give
the,
you the finger.
so
right?
2-2 there, if I go into 2-2 there, right?
Oh, yeah.
If I wanted to
This one
delete
right
two-
here, 2, 2.
the one that,
One,
oh,
1, 2, 2.
oh, 1-2, my bad, 1-1. I'm slow to make.
1, This one.
If
okay,
you
this
deleted
one.
that one, then the bottom one would point all the way up and the top one would point all the way down.
So you get this.
Yeah.
You can't get that functionality in a 2x2.
No, but
That's my point, that it doesn't test for that,
well,
so.
because that
How do we verify that
wasn't a
works?
scenario. No, okay, I think I know where you're going with this. All right, so let's get back into the big picture. Why are we, like, you're shoveling out the swamp, right? You're in the
Yes.
swamp, and you're like muck and it's
Yeah.
smelly stuff and leeches on you, and you're like, oh, leech, don't go there, right? And you're digging out
Yeah.
the swamp. And you're like sweating and you're cursing, and you're like going, why am I getting the swamp empty? I'm fighting alligators, why am I here?
Yeah.
Oh, you're looking for the plane wreckage that went down in there. You forget like why you're in the swamp, right? So why am I not giving you the unit test?
For
Right?
this specific scenario, yes.
For anyone,
That's-
right? So at the beginning of the quarter, I give you everything. And then as we go down, I give you less and less and less. I'm weaning you off it, because guess what? You don't get a pocket ed with you in the future.
Right.
Because believe it or not, in the future, you're gonna have a lot of problems that don't have unit tests. You still have to code it correctly.
Right,
So unit test is really cool because it like going, boom, that should be a null pointer. Boom, this is wrong.
yeah,
And if you remember your PA1, people are getting hit with every little edge condition there, right? Well, actually, I shouldn't even have to give you a unit test. I say, write a linked list, and then I grade you on that test, and I get like 2 people would pass and everybody else would fail, right?
Right.
So the unit tests are there to like, you did something wrong. As time goes on, I start weaning you off it. So the problems get a little more ambiguous, a little bit more looser, a little bit more vague to let you do it more your way. And the idea is that at the end, you're on your own. So at first you're riding a big wheel with safety gear. Then it's tricycle, then dad's running around behind your bike, and then letting go, then taking off the helmet. Right? So now you're like, running with scissors and X-Acto knives, right?
I see what you mean.
So the PA8, you don't get unit tests. Still, I have to adhere and write a good function, but I'm not gonna give you all the edge conditions. Now it's up to you to figure out those edge conditions.
Alright.
Right? Now, you can be, crazy and write your own unit tests or try to figure this out. That's great. Or you can just be very methodical and make sure you don't mess up. I'm gonna grade you against the answers. So and if you wanna like sit there, it's like, oh, I got this wrong, and I'm like, no, here it is. You reference a null pointer, say it crashed. Right? So I'm purposely kind of weaning you off this.
Alright, I see.
And that's intentional. Because otherwise, if I keep you on heavy testing, you're gonna kind of not be comfortable doing this on your own. And I think that's what's missing in academics right now, is that you need to work on an empty piece of paper. You know, like, you know, go create the class, go create things from scratch, instead of like fill in the blank, right? So I'm purposely doing that.
I see.
So on PA 8, you're on the hook for the real deal. You're not gonna get the unit tests. I'm gonna give you a unit test. Based off of the answers that I give you, like you passed 6 out of 8 or 12 out of 20, you'll know what you did wrong, so you can redo it for a regrade. But you're still not gonna get the unit test.
Oh, but we'll be told after.
But
Okay.
you'll be told this many wrong, and here's what notes kind of crashed on you.
What notes?
So you kind of have an idea of what you might have messed up,
All right, I see that. Okay.
right?
That makes me feel a bit better.
So PA 8, I would love to, so if I time how long it walks through a linked list, right? And I time how long it starts from here, and how long does it take you to walk to each one and get to the end, right? If I do 5 or I do 15, the time is so small because it's all in memory. And it's probably all in cache, so it goes really stinking fast, right? So if I wanted to test PA 8 from a timing perspective, I can't sit there and say, can you get to the node the quicker than the other students, right? Or are you fast? I would have to have 8,000 by 8,000 grid.
Yeah.
You know, then I would have to check to see which one are you deleting, and then how long did it take you to delete it? And it just would be a nightmare for me to get a very minimal return.
Right.
I see.
Right. So for this assignment, it's not about its performance, just because I can't create a test environment easily enough to do it. The real problem with this one is it's going to be, is it correct? Right? How do you get a 0 on this assignment? You know, I'll say 40% of people will get a 0. You know, we're like, what? You dereference a null pointer and you crash the machine. So if you do an exception, it crashes. I can't grade, it crashed. Right? You might get 9 working, and the 10th test, you blow it up, you got a 0 because it crashed. It doesn't finish the report, it doesn't do the stuff. And I'm not going to debug your code. So the biggest thing here is I'd rather you miss 1 or 2 and not crash. And so that's the thing here is, how do you crash? Dereferencing a pointer that you can't guarantee. It has to be real. It can't be null. So just make sure you do that. Second thing that people get in trouble with this one, infinite loops. They get stuck in one, like, I'm looking for something, and their logic's bad, and it never ends,
That's why I only have 1 loop.
right?
Because I don't want to have to deal with that.
So this PA is pretty straightforward.
No, I was just, I didn't realize that. That was my own question. I was like, oh, wait, that's only a 2 by 2. I'm like, oh, it looks like it should work. So.
All right, so PA 9 is an extra credit assignment.
I was like, what, another one?
Right, and for those who haven't taken this class before or know about this is an assessment question. So it's only 4 questions. These are the 4 questions I did in industry too. So if you have an intern with only 1 or 2 years of college work, 20-year seasoned programmer who makes $1 bazillion, I give you the same stupid test.
Right.
The weird thing is, you can have 10 years experience. I might evaluate you as having like no years experience, right? Because like, so you did, simple problems or easy coding. You didn't really stress yourself a lot. I've seen some people who have 1 year experience, but their experience is so much more mature and they've done really hard problems. It comes out in the test. So the test actually discriminates. So the test is this. There's 4 questions. 1, 2. Right? And the points are 1 point, 1 point, 1 point, 2 points. So it's a total of 5 points. So you can get 5% extra on this assignment.
Ooh,
And this is just extra credit, this is like in your pocket.
that's
What
good.
time we
But I'll tell you, this is an evaluation test, right, that I give. It turns out now, almost every interview, they'll give you a take-home programming test, right? And some places are kind of even, I think, snotty with it, where they you have to do it with a live camera while you're doing it, or you have to remote into there and they're watching your keystrokes. I mean, some are
I'll
like
just have a
crazy.
laptop open on the side. No.
But most of them are doing this, and the reason they're doing it is two things. Everybody says they can program, go program something. And it's a filtering device, just as like, I got 3,000 applicants, let's get down to 30, right? 3,000 to 30, it kind of tells you we're trying to get rid of 90% of the students or applicants, right? So this one here, same thing, right? Who doesn't want to work in the video game industry, right? Like I got anybody who's walked near a programmer applying for a job, right? And I needed to filter it down to say, these are the people worth my time to call them back. So I give a unit, give a assessment test. So to me, if you got a 3 out of 5 or better, I give you that phone call, right? Now, here's the catch. You can do this problem probably first day of class. There's nothing magical with this thing. I used to give this as PA1. Then I decided to move it to the end of the quarter, and my count still is about the same.
You want to measure our heads.
I remember the same amount of people get, same number of people get 3 or better, and same number of people get less than 3, right? It's about the same. So it's the same crappy numbers both ways. So I'm like, all right, I didn't add any value there. But here's the catch. If you do this honestly, I'm going to give you something that you will not get in industry. I'll give you feedback.
Ooh.
Too often you apply to something and it's like it goes in this black hole. They don't even, a lot of times they don't even email you back saying screw off and die. You know, there's this, it's like, what happened? And they're like, I don't know. If you didn't get a response, I guess that means you're not in contention, right? Now, from a HR standpoint, they don't like to tell you that you're wrong, you're out, because there's some legal issues there. The second thing is, well, maybe you didn't make the first cut, but maybe, you know, we're desperate. We're going to start going through the pile and looking at somebody who didn't get a good score. So they tend to keep them around, right? So what I'm going to do here is I'm going to give you completely detailed feedback for each question, right? So this is the one problem that I suggest don't share, don't work with others. Because if somebody else helps you, I'm giving your friends feedback. I'm not giving you your feedback. And think about it, if you're really doing this for a real job, it's going to be you. And it's really funny, good interviewing process, they give you an evaluation, they bring you on site. The first thing they do is they ask you something about the evaluation, and they can tell if you did it or not. And if you didn't, you're, I mean, door right there, right? So I'm gonna give you feedback on this. All right, it's only 4 questions. You can do them all. They're completely trivial. I was kind of snickering because it's that easy.
Is it wording? Is it one of those?
No.
Things?
So when I was in engineering school, it was really weird. I just give you one more story. They gave you a thing, and here's, you know, the problem, blah, 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 blah. And then here's like, put the answer here, you know, so many meters per second, right? And I would do all the work. It's a 5.5, you know, meters per second. 0. It's not in the box.
Oh my God.
Right? They said put it in the box. I didn't put it in the box, right? I did everything right mathematically. So like we never use numbers. We did equations. At the last step, boom, you put it into some kind of units and real numbers, right? So I did everything right, did all my derivations right, all my you know, crazy math stuff. And then all of a sudden I put the wrong number in the wrong variable, 0. And from my perspective, I hated the teachers that did this, but I understood and learned something. Engineers can't make mistakes, people die. Bridge falls in the river, buildings fall over, right? You don't make a mistake. A lot of times I will go against mathematicians and say, look, I will do this problem right and I will bet my car on it. Are you willing to bet your car? And they're like, oh yeah. I'm like, really? You want to do this? Let's play ball. Engineers can't make mistakes because people have side effects, right? So what they did is they gave us a sheet that said, follow these instructions. Of doing block capital your name, your phone number, all these different things, right? They say, you know, on every sheet, make sure you staple in the upper right corner, right? And they will this and turn in your sheet. So that was our homework. Go through this. And teacher gets, you know, I was in large classes, so I get 80 of these. It's boom, boom, 0, 0, 0, 0, 0, 0, 0, 0. And there's one, he goes, one guy out of 80. Everybody else got Fs and one guy passed. He stapled a one sheet paper
Oh my God.
because it said staple in the right corner,
Oh.
right? How do you get bounced out of assessments? You don't follow instructions. It's just that simple. If we sit there and say, give me the code in C++, it doesn't say machine code, it doesn't say SIMD, it says C++. So follow the instructions precisely. Because it's very easy. We're looking for reasons to pitch your assessment into the garbage. Follow instructions, right? All right. Here's the instructions. Yeah, I have to go. I did it.
You haven't posted it yet?
No, I haven't posted it. Oh, actually, I have it here on my directory now. What am I doing? Like, PA9.
Oh.
It is.
I don't know.
It's crazy.
It's memory. It's
Wait, what?
all right, so here's PA9, right? And it's absolutely trivial. All right, write this whole program optimized for execution and robustness in C++, not C, in C++, right? Submit only the CPP files, right? That's it. Here's the questions. First one is, write a function to do this equation. Next one, write a function to normalize a vector, a 3D vector. And some people got all kind of like, what is a 3D vector? If you don't know what it is, look it up. Right, I'll explain what this is.
No SIMD?
No, well, I said in C++, right? And you're like, oh, SIMD. Well, if you write SIMD on a MIPS processor, it looks different than SIMD on an ARM processor, which looks different than an Intel processor. So that's not C++, is it? That's hardware. It's not universal. All right. Here's a linked list. Remove a node. I'm telling you, this is amazing. This last one here is I give you a bag of points, XYZ. This function finds the maximum distance between any 2 points. Refactor it to also return the minimum. Right?
I think it returns both.
It says to also return the minimum.
I think, yeah.
Right? So those are the questions, are really simple. And what I give you is I'm going to give you the function, the files. And this way there's no typo. I'm going to give you the original code. So that you have the code. So this one says refactor, here's the original code, right? And that's your job, is to do those two things. Optimize for speed in C++, and robustness. Right. All right, so let's
Are we allowed to ask questions here?
you can ask questions.
All right, so you said return the maximum and return
Said also.
and also
Yeah,
return the minimum.
Right.
You also said submit only the C++. Does that mean delete
See
everything
everything
else?
So they're not, that's it.
Now you mean
So
literally return as opposed to set in the caller.
it's gonna be your call. You got some judgment call in here, right?
Okay.
But the word also is probably the key word because it's underlined and bolded, right? That means you're returning two things. Right? How you do that is really up to you. But the question I have for you guys, I said optimize in C++, clearly that's the class, right? What does robustness mean? Right? So give you a couple ideas. If you wrote code and you give me code, what if it doesn't compile? All you're returning is this CPP files to me. What if the code you submitted for your job doesn't compile? Would you get a good assessment or a bad assessment, right? So if your shit doesn't work, it's a 0. If there's you're missing a semicolon, 0, right? Am I gonna test your code? I've seen this problem 100 million times. I know I can point out like this won't compile, and I'll drag and drop it and like, yep, it doesn't compile, right? So make sure it compiles. So I would play with this in the sandbox, make sure it works, and then cut and paste it, and that's what you submit. So whenever you submit code, always make sure it works. Otherwise, it's really embarrassing, like really cool code, but the person isn't detailed enough to make sure it compiles. That's kind of sloppy, right? So what is robustness? We know what optimization is. We know it's in C++. It even says no SIMD. But what is robustness? All right, so the game we played at work was, if my code compiles and it crashes your code, you owe me lunch, right? So let's do square root function for instance, division, right? So let's say we had inverse function, right? It takes in a float, x, and returns a float. And here's the return. Right? What if I pass in -3? Does this function work?
It's gonna do an implicit time conversion.
Where?
Well, if you pass it -3, is it -3 an int?
-3. Last time I looked, at -3 it's a number, -3, right? -3. What, -3? Oh, here, -3. We'll do your integer first. Pass -3 into this. Will this compile?
Yeah,
Okay. Will it crash?
No.
no, yeah, because it's,
All right. What if I pass in a double?
no, because it's just.
Yes,
Yes, on what?
it will correct. It will throw you an error in the compiler.
No,
It will depend on your compilers.
it'll give you a warning.
Yeah.
Yeah,
Because you're
I'll put you in
truncating.
there.
I guess
you're
I'm trying to say your
truncating.
warnings.
Yeah.
right.
I've been training you that warnings are errors, but the real world, not a lot of people turn that flag on, which
Yeah.
is
Because I
sad,
mean, sometimes truncation doesn't really
right?
affect anything.
Now, what if I pass in 0?
Yes,
What happens?
because you're divided by 0.
So it crashes, right?
Yeah.
Throws an exception, right?
Well, would it actually crash? More so just return undefined?
Will it return undefined? Is that considered correct?
Well, in that case, yeah, because undefined is, you can't define
Is
anything.
that what the author intended in the rest of the human world, you think, right? So a robust function, right here, we'll do this one. What if I had some weird function here? Right, that did 1/x minus 5,
Oh, boy.
and I pass in 5. Right, then it's gonna be divided by 0, it's gonna throw an exception or fault, right? So robust means if I play by the rules and pass it anything, I get the right answer back. Right?
Right.
So let's look at something for a second. Square root function, right? What does the square root function take as part or argument? Double. It takes a double, right? Doesn't take a float, it takes a double. Right? And it returns a double. Right? What happens if I pass in -3? What was the return?
Should throw an error.
It's trying to create an imaginary number, right?
Yeah,
You know, plus or minus square root of -3.
Right.
Right, so there should be, I in there, right? There's no I, you're not
I
imaginary,
wouldn't know how
right?
to do that, would it?
Right? So this is not a robust interface. Right? But what if I told you that it was wrong? So like I give you 2 things. I give you the answer, like here's the answer, and here's the secret decoder ring that says this is a good answer, or it's a divide by zero, or it's a null pointer, or is this? I give you a little breadcrumb that you can understand how to read that. Yes, go ahead.
I mean, I know in Java you can do like a try block.
Exceptions don't work.
Okay, that's, I know you said that earlier. I was like, that's how I would handle it.
Exceptions really fall apart. Right now, we're thinking, let me go on my exception tirade. Here's a CPU, right? And you have one call that calls into another call, which calls into another call, which calls into another call, and this is main, right? If you do your try except, right? Or catch, I'm sorry.
I think it's try in Java.
If you do this, right? And if you don't catch it, it goes up a level.
Oh,
No, it rolls up the stack,
oh, if you don't catch it. Okay.
right? And if that doesn't do this, right, and that doesn't do it, then it hits main, then what happens?
You effectively did nothing.
It just crashes.
Yeah.
Right? What are you supposed to do with an exception? God, I always hate talking about this because I get such a religious war.
They're just stupid. There's no point to use them.
So here's what happens in reality. An exception happens. You know, an exception comes on the screen, people reboot,
Not my fault.
right? What you're supposed to do is try to recover. That's what the catch is for, right? Well, what if you had good defenses up front? Where you sit there and say, instead of recovering from dereferencing a null pointer, you prevent it from getting a dereference a null pointer.
Right.
What if you got a packet from the internet? So this packet comes into you. Before you use it, you scan it. If there's something wrong, you place in a dummy packet and let it keep going, right? So you can do a lot of defensive natures and get around this. The reason why the whole exception model is somewhat flawed is it's a single processor solution. You will be programming very soon on multiple processors, right? So let's just say there's 4. This processor here throws an exception. It can't handle it. Now where does it go?
Who knows?
Right? If you have all these 4 processors working together, and this is the lead, right? You know, so this is the boss. And these are like kind of the subordinates that are supporting whatever the boss task manager is. And one of them's there, it's supposed to actually report to the boss and say, what do you want me to do? You want me to kill that one or doing what, right? So as soon as you start going to multiple processors, now you got, do you have a true tree hierarchy? Do you have a matrix hierarchy? Do you have a grid? Are they not talking to each other? Was it on, now it's off because its job is done? Do I start a spin up of a whole thread and then walk away from it? So the whole idea of who does it boil up to falls apart when you get into multiple processors. And the reality is most of the time exceptions aren't handled correctly anyway. The better way to do this is be defensive up front. Make sure your code's robust, right? So let's do, let's write a function here. Trying to think of this.
Would the inverse and square root functions not useful for this?
Yeah, I actually had a question about one.
Yeah, let's do
The inverse one is
reciprocal square root.
Okay.
Oh, even more so.
All right, so here's a reciprocal square root. You're gonna write this. What's our parameters?
It would need to be a double because you're doing square root.
Really?
I mean, it could convert to a double, but
Right.
the robust way to do it would be, so it takes a double, I guess.
I wanted to return a float.
You'd have to convert it to a float after the square root though, that wouldn't
You know,
you?
you just do square root f.
Is
Oh, because you can do square root f, yeah,
right.
yeah.
Right, so we take an input, right, float. X, right, and reciprocal square root is 1 over square root of x, right? So that's going to be 1.0 f divided by square root f of x, right, equals some answer. And what's our return type?
Float.
Float, right? So that's not bad for first pass, but is this thing robust,
No,
right? So what happens when we pass in a 0?
it's gonna fail.
Okay, it's gonna fail, right?
It,
How do I communicate to the customer that it failed?
you would need to do like a conditional check if it meets a certain criteria and then return.
I guess I'm getting at is, what does the customer call?
Oh, they
so-
call.
Yeah, so they're looking for reciprocal square root. And they'll pass in some value
Can't
x,
you do a function identifier?
and then they're gonna get right here y. And so float x is 5.0. And then y, right? So we're returning it. What is the customer, when I pass in 0, right? So here, let me clean this up and write cleaner. Here's the programmer's code, float x, float y. All right, so. All right, there you go. All right, so the blue is the customers using it, right? The red is us, the authors, right? You pass in 0, right? The thing explodes. How do I communicate that that's bad to the customer? What's the clue on the customer? Other than it crashed.
You would need to somehow communicate that, well, X couldn't be in this case less than 0. Because anything less than 0 in
So
this
how
case.
do
would
we
fail.
communicate to that? Yes.
I mean, I think the C way to do this is we would set the return to like -1 or something bananas.
Okay, cool. -1. So if I had a return type as an integer, right? What does -2 mean? Is that the answer or is that a magic number?
Probably magic number. Oh, I mean, you could probably do something like, you know, the saved versions of like memcopy_s, where the return type is actually an error number. And so you return that, and if it's 0, you're golden.
So what is -3?
I assume, and then isn't there like a decoder ring for error numbers?
Right, as soon as you do that, you're getting into RTFM, right? Did we go through this before?
Yeah.
Right? Nobody's gonna look that up. Right? You know, read the fucking manual, right? Nobody's gonna look that up. So you need to make sure you write your code in such a way that they don't need to look it up. Right? So how do we communicate that this is wrong? Here's the customer's code in blue, our code in red.
Can you like clamp it so it can only take?
So now I give you a number, you just said, I ignore your number and I put something else in there. So you're not an honest broker.
You would have to tell them before the fact then.
How,
somehow.
this is the code in blue.
Could you potentially change the function signature to take a float pointer and?
Okay, flow pointer, fantastic. Now you take a flow pointer. Right?
Or, yeah, and that way
Okay.
you can, if it goes to hell, then you can.
Wait a second. So now what happens when I pass in a null?
It still fails, right?
You dereference to null and then crash, yeah.
Well, but
So
you can
you
check
can-
for that, right? So,
But how do I communicate to the customer, right? So the whole idea with robustness is the code works correctly and the customer knows what they're getting at all time and it doesn't crash.
I mean, if you change the return type to also be a float star,
Okay,
then if you return a null pointer, it's because something went wrong. You know, necessarily, the customer doesn't need to know what it is, but if you return a null pointer, something shit the bed.
so now you're basically saying, sometimes it's a real answer. And sometimes it's not a real answer. And by convention, because when I just look at the signature, I see a float pointer. Right? But you just have to know that, oh, wait a minute, sometimes when it's bad, it's null, like kind of like malloc, right?
Yeah.
That's the problem with malloc, is that you're using one return and you're using it in two different states.
Oh, I was gonna say, you pass a reference to an error code.
Okay, reference to an error code, right?
You know, as
in
an
the
error.
argument list, you're saying?
Yeah, and then they know that error code's there, and so they know they have to check it, so it's sort of communicated, you gotta do something.
Well, because like, I know that some compilers, depending like Visual Studio does this though, you know, if you're typing in like a mem square root, it tells you what you're taking. That's because it's a comment on this. It's a function identifier. Why don't
Right.
you just do that? Because then you say, hey,
No,
this
but
only takes whatever.
it doesn't matter what it takes, it will compile,
Oh, true.
right?
It will
You
compile.
can give hints, you can read the manual, it doesn't necessarily mean, you know, you're doing it right. The manual says, do not pass -3 into square root function. It will take it. Right?
Or don't let it take it then. Say, hey, if this is, just do a,
Well, you can't
why
create your own
can't you just do-
types.
why can't you do a conditional in the function itself? though?
Okay, so you do conditionals, but how do you communicate to the user?
You'd return something that says, hey, you
I'm
can't
getting
do
into
this.
that. What do you return? So we got the pointer game here.
You'd have to return
What, let's kind of go back here.
in some, whatever the error is called, yeah, whatever the. Whatever.
So
I
what
don't
if
know
we
the
do
different
this?
one.
What if we return success or failure? Right?
Oh, 0, 1, yeah.
Like a Boolean.
We do Boolean, right? Well, the problem with Boolean is there's only two states, true or false. Well, actually,
There's
you only have two states, false and not false.
right.
Because true can be 1, it can be -13, it can be 14.
So you return an enum.
You return an enum, because if you return an enum, now you can enumerate it, say it was a pointer, it was a divide by 0, it was a negative number. Cute, right? So if we return a enum, right, then now we're starting to talk here. So we have status.
Isn't that what an error number is basically?
No, error number is literally an integer,
Oh.
and you have to kind of go through a secret decoder ring to go after it.
And this is a not secret decoder ring?
What?
And this is a not secret decoder ring?
Because you actually can see in the
Oh,
debugger
like you see the
the
words.
name.
Yeah.
And if you make the names kind of intelligent, it will communicate what's going on there without doing this stuff, right? So you can make one success. Right? And you can have another one error. You know, divide by 0. You can have error. Negative. Right? So you can kind of give several choices here. If you have pointers, you can say null pointer. And you can give an enumeration on this, right?
Right.
So here we do status. Right?
Okay.
What's our arguments now?
Yes. to be a
Still be-
reference.
So now we have to return the answer. We have to take the input and return the answer. So now we can do float the input, right? And then float the output. Reference,
Right.
because you're gonna return it back from as an argument list. So now, when we use this, the customer should look at the status, say success, okay, I can read the out. Error, divide by 0, don't read the out, it's garbage. Now, we can walk them there, but we can't make them drink the water, right? And lead them up to there, but we can't make them drink it, because it's, you know, if they choose not to read it, that's our defense, that's our loophole to get out of the legal argument, right? It's like did you read the status? That's why that number is 0 or garbage. Right? So maybe you sit there and say, when an error happens, you return -1 in your float out, because it just doesn't make sense. How can you do a reciprocal square root and be negative, right? That just doesn't make sense. But you also have the error. So they read the error, they don't even read it. If somehow they read it, hopefully the -1 somehow breaks something else, and then they come back to this function, right? So for robustness, all we have to do is do not crash and communicate cleanly to the customer the behavior. Right? So how do we fix this? Now we're going to, inside of this, is we're going to have to check to see, is this negative? Is this not zero, right? And then return the appropriate returns on this. So same thing is true, anything that takes in a pointer. Some function, right, that takes in a pointer. Right? It's good practice to do a return status and tell you what's going on. What could be wrong with the pointer? The pointer could be null, right? What's also good practice? Cons with a side of cons, right? If you're just reading this, then you can put a cons here. Does the pointer change? Cons here. Do I need a pointer? If I don't need a pointer, reference. So check all your inputs in there, right? What makes sense when you're doing a loop, when you're doing a for loop, right? You'll see this happen a lot of times. People do a for loop and they'll sit there and say, let's do max. Max is 0, or they go, max is -1, right? Max is 1 minus 1. So they do the for loop, and then in here they go, if max is -1, new max equals something, blah, 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 right? Else, then they sit there and say, this is a new max and do this other stuff, right? So if this thing's looping 1 million times, you only go into this function once. These are one-time flags, making it -1, setting a flag, initialized, not initialized. And if you're looping 1 million times, I'm going, is it -1? Is it -1? Is it -1? I used it once, but I just called it 1 million times. So we never want to have one times inside your for loop, right? We want to make sure that anytime we return, you always return real data. So what if our code here, our number, it got passed in and it's -5. So we abort out of this. It returns the max. Max is -1. What's the distance between two players? -1. Does that make sense?
No.
Always return real data, right? That's valid, or communicate to them that it's not valid. So when you look at the homework exercise, now you start looking at it from a slightly different perspective, right? So this find maximum. Here's the number of players. So what this maximum is doing is this. Given a lot of points, right? Find the distance between each point. And which one's the longest? And then in this case right here, this one's the longest. So, so in that case there, what we'll do is we'll return that distance, right? So you're given an interface here that has number of players and then the array pointer, right? But when we look at it from a robustness standpoint, some things start screaming at you right off the bat. Are we changing the pointers? Are we changing the data of it? We're just reading it, right?
Yeah.
So
Cons, right? Keep adding cons, right? What happens when my number of players is -3? Right?
Well,
What do I return? Now you're starting to think the right way. So you got to start thinking about all these edge conditions. Because the goal is it has to be robust. It has to work correctly first. If it doesn't work correctly, it doesn't matter how fast you are. The second thing is once it works correctly, then you make sure it runs fast, right? So correct first, speed second, yes.
So, and just for this example right here, let's say we do what you suggest and we change the return type from float to status.
So how it works is this, when you, whenever you modify anybody's code, you bought it, it's yours, right? So like, if, think about it, I take my car in to get an oil change, right? Now my cooling light comes on. Who's at fault? You're gonna blame the mechanic that just changed oil, right?
Does it
But
mean-
he goes, but I didn't touch the cooling system. You're like, you touched it last, now my car is broke, you bought it, right? So as soon as you change one line of code, you bought the whole code. Right, so that means you can change anything.
No, I was just, so my question is, okay, let's say we change the return type from float to status.
Mhm.
And then we add an argument to find
Yeah.
max distance, it's like, float reference
Yeah.
answer. Cool. At that point, if we have a robust status that says, hey, you screwed up, here's your error, then the float reference is free to do whatever and that's still. gets approved.
It's on the customer not to read it.
Okay, so it's
Yeah,
like,
so-
once that status is there,
It's kind of like this, like,
float reference can say whatever the hell you
it's
want.
kind of like you're writing data, we'll just use PH7 as an example, you're writing data to a file. Right? Now, I know you all did this, wink, wink. When you did the F write, did you check your return code?
Yes.
Right? If you didn't check your return code and the write didn't work,
It's your fault.
it's on you because you didn't read the return code. Right? So when the litigation comes up saying your code didn't work the way it was, it's supposed to work, you're like, going, did you look at the error code? Did you look at the status? I always communicate correctly what's going on. It's not my fault you didn't read it.
So for PA9, we're just turning in text that you will compile.
You're just turning in a CPP file. That's
If
it.
we're changing a return code, it's not like we're breaking some test
No.
that you would be doing.
No,
or
there's no
whatever.
test. It's all by eyeball.
Okay.
Yeah, so I'm going to go there.
Yikes. Now I see why most people fail this.
Well, no,
You don't have
I'm
to
giving
do
you
it,
guys a
but-
lot of
Can
hints.
we go
Give you a lot of
crazy and
hints.
create our own test
You
function?
can do anything you want. All I want
It's
is the staple. All right,
Yeah,
the
yeah,
staple.
that's a
Alright.
very clear thing, I bet.
All right, so the a vector is, X, Y, Z. Right, to normalize a vector, you find the length of the vector.
Take the
Oh, right, that function.
skirt to the dot product.
Yeah.
Right? And the unit vector now is this, X over the length, Y over the length, Z over the length.
Wait, what
What's
is?
the U is unit product?
Yeah, this is the unit vector. You're gonna return a unit vector.
Which only gets you into trouble if you happen to feed it the zero vector.
Absolutely. Which, if you want to go, if you're math, you say there is such a thing as a zero vector.
There is a zero.
But
vector.
if you're in engineering, you're like, there's no such thing because vector has to have magnitude and direction.
Well, unless you feed us the same point twice.
But if you subtract two,
Right, if you feed us, if you're trying to tell us to find the minimum distance.
no, this is not this.
Oh, okay.
Minimum distance, there's no qualifications on it.
Right, because the vectors start.
It just say, here's a bag of points. If the points are all standing on top of each other, then it's zero. Still a minimum.
Because
So this is a different problem which says find
This is
the,
one. This is number 3. Or number 2.
this normalized
Like,
vector,
Yeah, given a vector,
normalize it, okay, that's
yeah, given a vector,
simple enough.
given a vector.
Okay.
Normalize it, create a unit vector. Right? Here's a function, right? For those who like this kind of looks like a Taylor series or Maclaurin series, how you want to look at it, depends on if you want to rub your eyes hard or not. This just says return, function takes in X, returns Y. That's it. Yes,
and so we don't actually need to put the A0 through A5 as arguments. They're just hard coded into the body.
the input says float, input is X, the return is Y. That's it.
And it says non-zero, okay.
Right.
I mean,
That's,
even if there are zero, it's not, you can divide by zero.
oh, yeah, but
I don't think there's any,
These are simple programs.
This
Like I
first
said,
one's-
it's designed for someone who's taken their first programming course to make it through. Or people who have experience, but I will give you all kinds of feedback.
and it's definitely 5th degree like that. It's not any bigger or smaller. We don't need to make.
That's the equation.
Okay.
That's it.
You're not about to change the degree of the function on this.
No, this is, it's.
Oh, God, if you did that.
I don't trust him either, but.
Right, you change the degree, like.
No, I'm not doing this. This is insanely straightforward. Alright, so here, remove a given node.
Hmm.
Just, here's a linked list. There's a head. There's this, remove a given node. That's all.
But if the node that's given isn't there.
No, a given node was parse the English. I'm not gonna
So
give you
you're
an
past-
imaginary node,
but you're
a
past
pretend
the
node.
node.
I'm gonna give you a node
That exists.
that's in the list and say remove it,
Would you pass as a null pointer?
right?
Yeah, but given node, you could just give us
But now
any
we get back
node.
to robustness. Right?
Yeah, because if you.
So if you pass in a null, that is legal.
Yeah.
Right?
Unless we're petty and we say, but we only take references, in which case you can't pass as a null. Is that robust?
Well, that's just another workaround, I guess.
All right, that's it. 4 questions, very easy, extra credit, don't stress too much, but I will give you detailed feedback. If you get 3 or better, you would get a phone call. So, so I want a lot of people to get 4 or 5s, right? All right, basics 9. Basics 9 is extra credit as well, because you guys picked the right door.
Alright, oh, it's OFCs, okay, that's already a no.
All right, so basics 9 is
Ooh, that's.
extra credit. All right, there's there's gonna be 2 things to fix in this one. First one is ellipsis. Probably easier for me to show you the code. Ellipsis is ... 3 dots, which says unknown number of arguments. Unknown number of arguments. So you're gonna write code. And here it is, ... Yes.
Is it assumed that all the arguments are ints? Like when I say int count,
They are, but
yeah, does the compiler know like, oh yes, and all subsequent arguments will also be ints, or is it free to do whatever?
no, it's actually free to do anything. That's how printf works. Printf has all kind of formatted string underneath it. But in this case, they're all ints. All right, so this one here says return the second max. And you're just gonna return it, right? So that's the whole thing. If you want to, you can use vector and algo if you wanna, make your life a little bit easier. I don't care, it's more about correctness. I'm really looking at, did you code this function right? Right.
Sorry, what's the second max?
Right, good question. All right, second max,
Second largest number.
second largest number. So here's a string of numbers. Right? The largest is 9, right? The second largest is 8, so you would return 8.
Oh, okay, that's.
Right, the thing is here, the first number here, count, tells you how many arguments. So in this case, there's 5 arguments. And so then, okay, and then the rest are the arguments. Now, which one's the second largest out of that string?
Same method signature as main.
So here's 10, right? There's 10. So then here's the arguments. When we look here, we have number 5 is the largest number. The second largest would be 4.
It's not also 5.
No, because it's not the second largest. That's still the largest.
Oh, because it's so you can be duplicates,
The duplicates, right?
so
So that's why I gave, that's all I did, yeah. That's why I gave you the algo and the vector as kind of hints, maybe if you want to. What I did is I just jammed everything into a vector. And I said sort with the algo. And then all of a sudden I can see which ones are
Couldn't you just,
duplicate or put it into a hash.
run through the list too, though, like, why would you?
Yeah,
need
you
to
can
get
do
that
anything you want,
complicated
but you're gonna get a lot of data,
Oh,
There you
okay.
go.
right? So here's the unit test for that.
Let's see how much data I said.
10,000 numbers.
Right, I just did a couple.
It's like, if it's 10,000 numbers, that's,
You'd have to
I
type
fully
in
expected you
10,000
to do to give us 2,000 numbers with the random seed you already knew.
That would be kind of, well, two random seeds, one that's larger and one that's second larger.
Sure.
right?
you kind of just.
You know, you're, I like the way you think. That sounds pretty evil.
I'm so fucking sorry, everyone.
No, I'm not saying do that. Yeah, I'm not gonna do that. But now you got me thinking. No, because your argument list can only be as big as the stack can handle. So ellipsis has a limit because of the stack. All right. So now here's what's weird. There's two programs in this thing. There's ellipsis and there's parse. So when you work on ellipsis, you go in the ellipsis, right click, and it says startup, set as startup, and it becomes bold. And runs this. We want to work on the other program, you click on parse, right click and say set startup. Now it's parse, right? And what is parse? Parse is pain and rare suffering exercise. And what you're going to do is you're going to parse the command line.
Oh.
So when you saw main, right? So here's main. A lot of people don't know how to do this. Here's main. There's this argc and argv. Those are command parameters. So you can actually start passing. So this thing will compile to an exe, and you can type in exe in your thing and give it parameters. Those parameters get added. So when you do a think about like if you're doing a help function on a Unix command, right? You'll do man, right? -h and then the name of the function. The man is manual. Then -h is a flag. Then another field is, I'm looking up, remove, right? And you look up remove. So those are parameters that go into the function called man. So I'll show you this in a second. All right, there is a couple parameters here. And I'm trying to give you something a little more real. I'm giving you a chunk name. So here's different types. Verse, norms, anim, texture, UV. I was in a graphics mood. And what your main function does, it returns 0 if it's success.
What, no status?
No, the main function. This is main from every function has a function called main. Let's see.
Yeah, no, I'm teasing.
Right. And -1 if it detects an error. So you're going to be parsed with variable arguments. Right. So you're going to go -t chunk name or -n, chunk type and chunk name. The name can't exceed 20 characters. Right. So here we go. Parse -t UV type n player name. Or you can do -n player name -t type, right? You can have the -t capitalized or not. You can have the -n capitalized or not, because sometimes people leave the cap locks on, right? But here's one that's not right. Here's -r. We don't understand what an R flag is. -n for name, the name is too long. There's too many characters. -t, the norm is supposed to be norms with an S. Or here, we're missing the name altogether. So these were all returned -1. Right? So how do you debug this? This is a little bit tricky. So first thing is right click here and say parse, right? And you want to start project, and you know it because it turns bold, right? So now you can compile it. I'm just gonna put a breakpoint in there just to show you that we're in that code. Boom, right? Now, how do I debug this? How do I develop this? Solution, go in here and remember when you guys were going through all the different settings? I think it was PA5. Properties, there's a field called debugging. And you see arguments, you can sit there and say -x, astro -j Jane. You know, dash, you know, Z Jetsons, right? So let's say that's my argument. So I just say, okay. Now, when I break here, boom, it just funneled in the string. So how do we look at the string? Go here, I always use watch window because it seems to be the best. Add watch, boom, here it is. And then add watch on this. Boom. Okay, so what is this? 7 says there's 7 arguments, right? V, here it is, and there's the first one, right? You don't really see it. We open this little window here. There it is. This is the first argument, right? It's a little hard to see. So let's look at it this way. So the trick is here, right? It's going to sound weird, but when you see an array in the debugger, let's see this array. It doesn't know how many. You just say how many. All right, there's 7. So you just put here, comma, 7. Boom, right? Now when you open it up, there's all 7.
Oh,
Comma 7 is the size.
It's how many elements in that array.
Yeah.
and the first element is the location of the compiled.
Right.
Okay.
So how the arguments go, it's really quite simple. Let's say we had a function called, we compiled something called PA8.exe, right? And it takes in an I'm sorry, this would be basics, right? So basics, basics 9.exe, right? And then, minus T and right? So when we see this, right, this is going to have 1, 2, 3. So the count is 3. What you're really going to get is slash ... all the way to your drive. So you get the full path. So you're going to get 3. So this is 0, this is 1, and this is 2. So your arg v is going to be ... basics 9.exe, and then this will be -t. This is vector. So that's how it's parsed. So when we look at this, I typed in 7. So the first one here, you can click here to see the name. Maybe. There it is. Blah, 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 parse.exe. Right. Then this is my -x astro, -j for Jane, and Z for Jetsons, right? And then now you can start parsing this and doing your work here to see if it's valid, return 0 or -1. Right? And then when you want to try something else, let's say you want to try one of the unit test ones. Go to the unit test. This is in the ellipsis directory. And you can just say, I want to test this one. I think that's weird. What is that character? What's this guy foobar there? I'll say. Really got screwed. All right. All right. So what you just do is, if you want this one here, you say, here's my arguments. And now you can test drive this by going into your parse and go into your properties and just add it right there. So now, right? And then this is now giving us 5, so let's change this number to 5. There's dash T, all this stuff. So you get to parse this and kind of look at the stuff here. You'll have to write a couple functions to make this work, but it's not bad. What's nice about this, once you get over this part, this means you can make any function take in parameters. And it can be, now you can write actual command line items that you can use on your own PC to do things. So it's kind of cool, right? So that's parse.
What do we need to do? Just return an error if
Yeah,
the
just-
arguments are not valid?
It's a 0 or -1, but you have to parse it to see if it makes
Yeah.
sense. But yeah, just kind of get you in there. Okay. Any questions on that? So this one's a pretty easy one. So hopefully you can get some extra credit points. All right, we were doing the particle system. No, I did not. I am such a stooge.
Yeah, I wanted to ask about that. Because I was, the data alignment,
Yeah,
For
we'll
Cindy,
go through that in a second. Hold on.
Yeah.
I gotta get one because I'm such a stooge.
oh, I didn't. It was over my head. I'm ready to. I'm gonna be gone.
All right, so I did not upload this correctly, so I apologize. All right, so here's the particle system, and we're gonna talk about profiling and how do you measure the timing and performance on this stuff in a number of ways. But there was questions about SIMD, right? Was that the?
Yes, I was talking. in the meeting
Okay,
class, but-
so SIMD, what is SIMD's role? SIMD's role
Data.
is, it has to be aligned to 16, right?
Yeah.
So we have that whole union structured game, right, where we have an underscore M128. And the name of the file thing is M, and we union it with a structure that has float X, Y, Z, W.
Oh, and that gets the 16, I see.
Right, no, that's not the whole story. Right, this is the union. Right, so this is our data. And what this means, we can use the underscore M or the XYZ, right, interchangeably. So when we're on a stack, right, so I'm just gonna do some function foo. Right, when we declare it here, we go vector V, right? This is going to basically point to that, and it's going to be aligned. It's going to be aligned because of this guy here, the M128. This guy has something kind of weird in it. It has a alignment declaration in here. It's a declaration spec align 16. So this basically says force it to be 16 byte align, which is 128 bits, right?
And
Cool.
is that a keyword or is that some kind of preprocessor thing?
It's a keyword. It's a preprocessor thing. So let's look at this. I don't think I have it in this one. No. So
I think if you F12 on it, it goes there, right?
here's. So this just guarantees that it's aligned, right? So let's look at one vector here. Right, so here's the union. And if I go into this.
Can you not just view the code?
No, I should be able to,
Yeah, I know, I was looking at it on my,
right, so I don't know why are you not giving me. Oh, you bastard,
ooh. External. What?
something feels wrong here. Huh?
It's what?
That doesn't work on mine either.
Why is it not in the class though?
All right, well, I know where it is in this guy right here. Fine, I will find
Oh,
you.
that's where I saw it, yeah.
Yeah, oh, here it is, right? So, here we go. It's right here, an M128 is a union of all these guys. But then it has a declaration spec that says aligned to 16. So
And that's a keyword?
you have to use this whole combination.
Oh, and each one of those says, hey, you can have 4 floats or 2.
Right, yeah,
unsigned
this is like, how do you want to read this? We'll read it as 4 floats. We could read it as 16 byte integers. If we wanted to,
Right.
right? So, but that's really neither here or there. This guarantees. Alignment to 16, right? Because it's on a stack. So that guarantees we on the stack. All right, so now here's where we get into fun, right? If you did this, vector star p equals new vector, right? You're gonna get a p. P is a very, it holds a number. That points to a chunk of memory, right? And this is gonna hold 4 floats. Right? This address has no guarantee. Think about with your memory system we made here. What's the guarantee that we get? We get some of this 4 byte aligned. It may happen to be 32 byte aligned, it could be 8 byte aligned, but it guarantees to be 4 byte aligned. So when we call new, we get into trouble. Because it has to be aligned for it to work. If it's not aligned, it doesn't work. So last week, we talked about overloading new and delete. I told you the trick is to vector is to basically use a class here. And I created a class for you called align 16. And what it has is new, delete, and these are guaranteed to be 16 byte aligned. So if you just derive from it, what will happen is when somebody calls vector star p equals new vector, it goes new, is there anything in this class? No, go up the chain, oh, here it is, use this guy. So when we derive from align 16, now our allocations will be aligned. Yes.
So I did it with the stack allocation originally, and it threw me a read access violation error. And so I did some digging, and my working theory right now is that, so I basically did it as like, I loaded the scale in one of the vector 4D ones and said, okay, make an M128 where it's a scale 4 times, multiply, like do an MM multiply of that
Right.
times my vector.
If you have to start off with an aligned data.
But if I initialize it on the stack, it's not guaranteed to be initialized.
And only if it has the underscore M128.
Right, no, but I went into I changed the definition of vector 4D to be an M128 unit.
You basically lifted the one that we had from.
I did exactly that.
Okay, cool. That's what you should do.
I did.
Yeah. So
I did that. And even then, so even, so I changed it now and now it's compiling and working, but for a very long while, I basically said, oh, so I did that
Okay,
in the .h file.
right, so now all that means is stack is correct.
Yes, I don't use
Local
new,
variable.
I don't use new.
Right. And you have to make sure it's floats and all this sort of stuff.
Yes, yes,
Cool.
I did all that.
Now, if you pass it to a function, you can get screwed.
That's, okay, why?
Function pushes data onto the stack, right? No guarantee what the alignment of the stack is.
So if
So
you,
the calling, remember when, so now I'm going back into like system stuff. When you call a function, right? So foo A, B, and C, right? Let's say you call this function. You go, call this function. What it's going to do is it's going to take the stack pointer, right? And now it's going to say, hey, I need to push A, B, and C onto the stack. And then when it goes into the function, the function goes boop, 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 pulls them back off the stack,
right,
right? If you pass by value, you're potentially hosed because it's not aligned. All you could do is call functions you pass by pointer or reference.
so I did that, so I thought that I had that issue, and so I put like, I literally wrote in my original version, like, do mmul ps of this times my loaded vector, and it went, nope, read vax is violation. And I'm like, did this vector get pulled out of alignment by being passed? I don't.
No, this vector, which this vector?
The vector 4D this.
You gotta put a check in there to make sure it's aligned.
But if
You're-
I defined it in my struct to be aligned,
You have to follow the data all the way through. Is your vector sitting inside of your bigger class?
I don't understand the
Is
question.
scale inside of the particle class?
Scale's a float.
Whatever the vector is, are you using it inside of another class?
It's, I think, potentially part of the particle emitter class.
Right. So now that particle emitter class is not aligned, then that knocks off everything else.
So the way I ended up solving it was I actually initiated, like I initialized two new temp vectors, one of which was the loaded scale and one of which was a copy of this, essentially.
Right, because you're now putting it into an aligned space.
Yeah, on the current stack frame.
Right, yeah, you have to, everything has to be aligned. So
It's petty.
the way this works
So is
is
that the
this.
proper way to do it then, is that you have
So,
to create two?
Here's the thing, if you play with everything on the stack, right? Stack meaning you're inside some function. You can just declare the vector directly. Right, this is good. This is basically PA6. If you notice, I had everybody work on the stack. Now, if you want to, and this is the vector, this is using the PA6 vector definition, right? With MM128, right? If you want something dynamic, right? You have to make sure you create a vector class. And you derive from a line 16. Right? Now, one more caveat, you cannot have a virtual method in there. If a virtual method has a V pointer, it knocks everything out of sequence, right? This line 16, I gave it to you, you just don't know you have it. It's been there all along. So like Wizard of Oz. So if you could look in framework, you type in a line 16. There it is. So there, this is the align 16 class. So I overloaded the new and the delete to handle 16 by alignment.
So
Yes.
you would put.
All you do,
line 16
all you do
in
is
the
just derive from it.
file?
Yeah, public.
Yeah, just do a derivation.
And then it's not
Just
necessary to do
derive
something.
straight from it.
Oh, so like you literally just inherit.
Inherit,
a dot
yeah.
H, you just do, oh,
So,
instead of doing what you had for Cindy, because that was some,
yeah, so you basically take your SIMD vector and then up here you just go.
Oh.
Public. Line 16. Done.
wow,
That's
okay.
it. And
Then
it
it's
will
okay.
automatically work. Right. So now that gets us further, right? So this is dynamic. So this is heap. This is stack, heap, right? And now the last one, when you want to pass in a pointer, right? So you created a vector here, vector on the stack. You want to pass it in the function foo. You pass in v, so you're going to pass it in, right? This has to be a pointer or a reference. Because the stack itself is not aligned.
Right.
And that's will get you there.
Oh.
Right, no virtual tables, right? So no, v table on vector, right?
So to be clear, that original declaration
It's totally.
is aligned. Over on the left where you said stack, vec v,
This is aligned if you use that underscore inside it, yeah. And this is aligned because we're doing a derivation, we're derived from the
Right.
line here.
but the copy,
And
it is
a
a copy.
copy just copies 16 bytes.
So the aligned is not
It doesn't,
really,
it's not
it's
honored.
not really part of the type, it's.
No, it's not honored on the stack. It's a pass it by pointer or by reference.
So you still have to pass it by point of reference, but the align
Yeah.
16 inheritance.
Because
just
if you
allows-
think about it, if you pass a pointer or reference to a stack, to a function, you're passing an address.
Oh,
Yeah, you didn't move your
Yeah.
data.
You didn't move your data still is aligned. Then when you're inside the function, it goes, oh, I'm still pointing to that data over there that's aligned.
And then you can just do,
And it just works, right?
there's like 2 times faster for all your matrix multiplications right there. yeah.
Maybe,
Well,
maybe.
it
Right.
should.
And then one other caveat. If you have particles, right? Right, or emitter, whatever you want to call it, and you have some crap in here, and then you have also vector, v, right? Now you're screwed. Because the particle is an object. When it calls new on it, it lands in some location. That doesn't mean this vector is aligned. So never have a vector buried inside a class. So inside a class, what you want to do is this. If you put your particle and your vector inside a class, put vector star PV, keep the pointer on the class. And this way, when you call new on particle, it just holds the place for the pointer. Who cares if that's aligned or not? Because the data is what has to be aligned. So did you get that last part? So this is bad, right? This is bad,
Yeah.
right? So you want to have pointers. So to do something in the line, you have to have the pointer aligned. You have to make sure you pass functions that take only pointers or references. You gotta make sure you're inherent from it. Make sure you're using the m
Now,
underscore
If
128.
there's a function in particle systems that takes value, can we change it so it takes pointers?
You can do, like, which one is that? I mean, like, it's.
So I haven't looked at it. that
Basically, you
too
can do
much
anything
yet.
except the OpenGL.
So we could change anything. It just has to work, so.
Yeah, well, and the timing and everything else, don't radically change the structure so much that the main loop doesn't look like the main loop.
Okay, yeah.
So I got to the particle, the thing in particle editor, that the execute function, that's a hot disastrous mess.
Mhm.
That one, are we allowed to freely rewrite that?
It has to preserve the same behavior,
Sure,
So the math needs to stay the same.
yes,
follow
which uses function, random functions all over the place, right? Random functions are slow, but here's the catch. I'll tell you one thing I did, I thought it would speed it up, it didn't, so just save yourself the day and don't do what I just did. I recorded all the random numbers into a file and then turned around and just said, read the next one off the file.
Oh, God.
It was slower. So that didn't win. I figured, I'll just record 20 minutes worth of random variables, and this way it repeats the exact same way and looks right. Wrong answer.
So just to kind of get, so I understand what it's essentially doing. You're essentially, this pointer plus plus nonsense is basically just going through and updating the X, Y, Z, and W variables, which I understand. My question is why, so at you're doing this random thing where you're multiplying the variance by either -1 or -2. Yes?
I have no idea. It's magic happens in that function. I mean, like, I'm not memorizing it. It changes all the time.
So you change it like every
Yeah.
year, so.
Just for funsies, it just does numbers.
It does number, and it has to be faithful to those numbers, otherwise you get different behavior.
So it,
But like, why though?
You can't get an approximation. Remember, your job isn't to, look here.
but that's.
You know, like,
the
I'll take my
biggest-
particles, when particles are rolling around in a whirlwind, right?
Yeah.
Like, when, you know what, I can make it really fast, they all stay still.
Okay, well, that's
Right?
not,
Right.
Did I
Yeah, that's
optimize it or did I change it? Right? I
depends
changed it.
on your definition of optimization.
So it has to still preserve, right?
But at the math, so you would need to do some like
Every
crazy,
single math operation has to be preserved, you just need to do it faster.
that's a lot of random logic, that's not fun, oh.
Well, but that's kind of how things are, right?
Yeah, that's-
Yeah,
I understand what execute is doing.
Oh,
It's just-
yeah,
This is a hot mess.
it's really that, yeah, it's
Complete hot mess.
it's bad.
It was saying what, emitter?
Yeah, it's in particle emitter and it's on line 280. Yeah,
Yeah,
this is
yeah.
hateful.
God.
Yeah, no, this is a shit storm, and
Why? But like, why though?
I'm
Why
just
are we
telling you
doing-
that, that's how it was written.
Okay, but how do we like optimize random numbers? You
You
can't.
really can't.
Yeah, you,
No, what the hard part you can optimize here is because they're doing this nonsense where they're doing, you see that sources like TPOS plus plus T, like TVAR plus plus. What these motherfuckers are doing, which is super fucking annoying, is
Right at
they're-
that point of the quarter. The filter's off.
yeah.
Okay, well,
I'm over it.
I come from industry, so swearing is caring, so I know you're invested.
No, I sat here and like when I had this aha moment of what is happening here, it made me so
I
mad.
didn't write this, so don't.
No. What these motherfuckers are doing here is so
Wait, right here.
I'm not bitching at you, I'm informing people so they don't.
Yeah,
like, spend
no,
the
let's
hour.
hear what you're saying.
Yeah, no, I'm not complaining at you, I'm informing the listeners. What they're doing here is that they're accessing this block of XYZW data. And essentially they're walking the pointer one float at a time along this array instead of just using like vect X, vect Y, vect Z. And really, you don't even need to do that because it's actually an M128 and you can just, sorry, it's fine. It's a ridiculous thing.
That's
to
not
do.
fun to rewrite, that's.
It's not fine.
Yeah,
Wait, and it's multiplying the
unwell.
pointers?
Yeah,
It needs grippy soft time.
Why is it multiplying pointers?
When I figured it out, I hyperventilated. I was like, this is so maddening.
Not surprised.
Wait, so where did you get this random,
It was a coworker writing, who wrote this.
did he write it this bad on
Yeah, he
purpose?
wrote that part.
Oh, you told him to write it as bad as he
No.
can? Oh,
Oh, this is in earnest.
This is real. You said who?
This is in earnest, like it's sincere.
Oh, yeah.
what,
No, I'm telling you, you're just,
what kind of computer is this running on where like you would think, oh yeah,
No,
this
no.
is fine?
majority of this stuff is his, and then I added some like Easter eggs for you guys.
I don't like.
I didn't, trust me, I didn't touch this thing. I'm like, oh, this is a shitstorm. Just don't bitch at me.
I mean, it's definitely
I'm bitching
like,
at
why would you
that.
need the preciseness of doubles here first off? That's just,
Literally the worst pointer arithmetic ever. Like people talk about like, don't, please, for the love of God, don't do this.
if they say, yeah, you
Alright.
shouldn't want pointers, that's.
So,
Yikes.
so let's talk about profiling, all right?
Right.
Can we argue for a bio break before we?
Yeah.
What?
Can we take a bio break?
Oh, yeah.
Let's do a break then, all right.
You got a sandwich? Well, why didn't you eat it before?
Oh,
You just eat dirt.
Who called me? Oh, no, I don't want to call them back. Yeah, you know what? I will. That might be important.
No, you're fine. I didn't. I'm feeling like you're.
Well, you're in the corner,
I'm in
literally.
the, yeah, I'm in the
I mean, you just
corner.
want to swap.
I'm just gonna take the whole table line.
I
Put it into the oven.
Let's figure in that same. And probably go out.
I've been carrying around my fucking
Same and
dust cover today because of the Memorial Day ceremony.
Oh, yeah, that's right. I almost forgot I was more worried until my friends are still in, were like, oh, it's a 4-day weekend. I was like, what? Oh,
It's like, yeah, make sure you actually know what it's fucking for, because people tend to forget it.
Yeah, it's true.
It's pretty depressing.
I just generally lose track of all days now. There's nothing to hold me to.
If people are looking at this weekend as another reason to get a day off to work to drink.
Yeah. Yeah, it is. That's usually what a lot of people do.
We also have the test.
Yeah, it's like, no, it's not the case.
Oh, yeah.
Remember why? This is people that are, that some gave, people gave some, but some gave all. I read the prompt about the missing man table. At the event. Talked about what every item is for and what it means.
Do you guys do that in like every facility? Like we put in like every single like public facility.
But yeah, at least here, I mean, it's not like it's permanently set up. It's just on Memorial Day and Veterans Day, we will do a missing man table and flag folding ceremony from the Veterans Department office, so. Yeah. We kind of messed it up today, and the two people that were doing the flag folding, they had the flag backwards. But we were able to kind of play it off because typically on uniforms, if you had the flag on it, it's backwards.
Yeah.
So like you wouldn't think twice about it because a lot of the veterans are just like, yeah, we didn't think about it until afterwards, and somebody that wasn't a veteran was like, wasn't it supposed to be the other way? And we're like,
It happens. It happens.
Like, this is
As
why-
long as you don't drop it.
yeah, no, they didn't drop it. It's fine.
I haven't done that in years. I haven't done that in like at least 10 years.
Yeah. I've literally been carrying around this
Oh, nice. Okay.
just because we put like 3 different covers on the missing man table representing like the different branches of service. There's this one from Marines, there was one from the Army, like an older style Army one, and one for the Navy.
I don't think I ever bought one because you wear ours hardly ever, and we don't even wear our blues.
Carrying around my dress cover all day for Memorial Day. Yeah, in Lincoln Park, we did the Memorial Day commemoration. That's good. We did like little lunch, and then we did a missing man table thing, and we talked about all the items on it, and then flag holding ceremony.
Be very careful not to touch it.
Yeah, no, I've just put it in a plastic bag and then that bag.
And put it in a cardboard box.
Yeah.
Right. Yeah, that emitter function, the one that you just put up there had made me like actually, I was like screaming, like, did you really do this?
I love it. It was like, I didn't write this, don't bitch at me.
It was a pointer walking through a float that was part of an 128. Is that what you said?
What they're doing is essentially like they're updating the position and velocity of a particle after like a time beat in a random way. And so what they're doing is they're going essentially like, okay, update the X, update the Y, update the Z, and then do the same thing for velocity, update the X, update the Y, update the Z. Except, so let's, of course, X, Y, Z, and W are stored as a vector, right? And instead of going, oh, update the X, update the Y, update the Z, they're like, point to the X, update that number, move up 1 pointer. And so
So it's
obviously now-
ignoring the structure.
Yeah.
It's like it's walking through the structure.
Correct. And so like now I know it's pointing at the Y, update the Y, pointer plus plus. I'm like, and so I'm saying like, why are you doing this pointer plus plus method? They're just literally walking through the data like an asshole. I'm so mad.
Yeah.
What fucking video was that?
Ed mentioned the obfuscated C code contest, right?
Yeah, this is up there.
One of my friends, every Christmas, he would send out a winning contest entrance from one year, and it's this, you know, square block of gibberish that when you compile it and run it, it prints out the words for the 12 days of Christmas. And it's like, there's no way you can, no way.
That's just like self-imposed penance.
Yeah.
Like why? Trash.
So you're gonna get home to a house with no power?
They just sent me a text message saying, the power just got returned, so.
No, that's good, yeah.
Yeah, it's been out since 1 AM. I was gonna work on homework all day, but I was like, or all day, but I couldn't, there's a power. It said, came all the way over here early.
No.
Trading, the markups, all this stuff. It was like, yeah, wait, but it's interesting. It's like fun facts. Oh, yeah. Well, all I know is that when I went through all that. Rank hanging out my crap. It's like, I didn't have the money. Right, yeah. I don't know. But people, it's like. It's just a note, you don't hear like major updates, right? Major
Spread out a little bit.
Yeah, I was feeling a little.
Are you going
compact in the
wide?
corner.
Boom, was it?
Playing the hardest thing I had my knee on today. Sad part. Right, it's color blood.
I hate that class.
You really do.
It's dumb. Really dumb.
Which class?
It's a programming language concepts or program language concepts. It's just Scala. It's dumb. I hate it. It doesn't, I'm not gonna use it.
It's all Scala or?
All of it's Scala.
That's like the only option you had, was just Scala, or,
Dude, literally, that's the entire class.
oh, wow.
Yeah,
You could take one of
Got some
that's all it's in there.
pretty serious programmers at work that love Scala. I mean,
I think it's weird.
yeah.
I don't know. Just the way it works is weird.
You don't like functional languages?
It's functional, right?
Yeah,
Yeah.
it's very functional.
Yeah. It's, I guess, just like, because I'm so used to like, doing Python and then Java and now C++ and how very similar they are.
Functional is weird.
And then Scala's
I
out
love
of
functional.
nowhere.
I love it.
Yeah.
I don't know.
We're really eased into it, so.
I mean, the thing is like the homework is not that bad. I mean, it's really straightforward. He damn near tells you what to write. And then quizzes are not that terrible. Then the midterm was like, fuck you.
Yeah. Which class number is that?
347.
Okay.
Yeah, CSC 347. Yeah. Corin Pitcher, he's a great professor, like really cool, really nice, really knowledgeable.
Class.
Just the class is weird.
You know, I believe you didn't clench your teeth when you said it.
Right. That's basically what I'll be doing tomorrow at work, because I'm gonna be sitting there for 8 hours.
I'm doing PA 8, 8:30 tomorrow, probably.
Yeah,
Because now that I know actually how to do it. it's gonna
I
happen.
am still very much at the beginning of it.
You had basic, like, he basically went over.
I
how to do
know,
it.
like I get,
Like
I
4 points.
I get what it's supposed to do. I understand what it's supposed to do.
Yeah.
I was just trying to write
I
the
have no
code.
idea
for it.
why. Oh, you expanded your
I want the whole table.
It's the seated from work.
The one with the table.
I am the table.
Pointers are 4 bytes, right?
I am 32-bit mode, yeah.
It makes more sense for me to just,
Why?
I felt very,
Do you have your card today, by the way?
sorry,
Like, well, no, I have to take the red line anyway, so it's a good thing.
why specifically? the other one?
You know,
Summer again?
You'll-
Yeah,
You wanna get fucked up?
no, I have to go to Wisconsin. We're going to Wisconsin.
What?
We're going to the Dallas, yeah.
Hey,
We're leaving tonight, so I gotta get there.
Jesus, all right.
Yeah,
Are you just going all the way north?
no, we're going to Sheffield. I'm going to the place.
Oh.
And then you can show from-
Okay,
Yeah.
gotcha.
Wait, I have to take the red line in.
Red line.
Out of curiosity, so I see you have this particle class. It has a ton of stuff in it. Yeah, great. So I would like to,
That's where we're back on.
That's kind of how things work.
Okay.
I can wait 4 minutes also.
No, that's fine.
So unfortunately, I need, if I want the whole, even if I make the whole class 16 byte align, which I can do if I just inherit publicly from a line 16, blah, 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 right? It does it automatically as you put it, yep. If of course, it lays out the data in order, so if I have these 2 pointers at the
No,
beginning.
you got to now align the internals. You have to add correct padding and shuffle stuff around. I wouldn't do it.
Oh, we can pad.
You can do whatever you want. You
Oh,
got
sure.
the structure, right? I'm telling you, the better way is not to worry about the padding, is just put a pointer in your structure.
Yeah.
Oh, I see.
That's what
Yeah.
this is right here.
Hello?
Because otherwise you're trying to line all this mess, which is a shit storm, and you change one line of code and the whole thing breaks again. Just put a pointer there and it points, and so your memory is really like this. This then goes out to a block, and this is aligned. And this is just a pointer.
Yeah, but the particle, so in your code and particle emitter, you say you call new on particle. Right?
Yeah, that's new to this box right here.
Right, but that means that the particle is on the heap, like the whole data structure particle is
Yes.
on the heap.
Mhm.
Right? And I don't think you're telling me I should go through all like the vectors inside of particle and make them all pointers.
Yes,
Oh, I should.
that's what I'm saying. Then you can't get screwed.
Interesting. But then I'd have to change the initializer or the constructor.
Yeah, it's called coding.
Shit.
Yeah, go for it.
Do it, do it.
You mean, I want to build a house, I have to dig a foundation first?
No.
You know, I have to remove rocks and dirt that's in the way.
Earthworks.
Yes, that's what happens. You'll get there.
Yeah, but do I want to?
All right, but the question there is, you shouldn't necessarily go after SIMD yet. That should be your last step.
Oh.
Did you squeeze as much out of everything? You know, so, all right, so let's talk about a profiler. There's 2 different types of profilers. And I got lecture notes on this too, but we have statistical. And we have instrumented. Right, so here's your code running. Let's just imagine here's your code running. And statistical just has a little timer. And it goes stop, it goes, hey, what line are you on? Timer goes, stop, what line are you on? And it samples so fast, and historically, if you're in a big function that's slow, you'll get a lot more samples in there. If if the function's called once in a while, maybe the sampler just missed it. It got called and it got the strobe hit before and after it just missed that function. But a statistical thing has an advantage of it's correct. It's accuracy. Accuracy is low, but it tells you correct information. And the reason why I say that is we don't change the program. The program runs, you just can take an EXE and runs really fast, and it samples and tells you the data. Instrument code says, here's all your code, right? And then here's a function that says math, multiply, right? Here's some code. And when instrument does, it goes register, start, and then right it leaves, register, end. So it does this to every single function. So it's very, very accurate. But it's not as correct as you would want it to be. The reason is this code here takes cycles. And that cycles could knock your cache out of there. It can change your flow of everything. So we have this trade-off of, do I want it to be very accurate? Or do I want it to be behaving correctly but with less accuracy? So an example of this, let's say in 10 seconds, I can process 10,000 particles. Well, in statistical thing, I will be processing 10,000 particles. In the same time, I might be processing 1,000 particles with the instrumented one. The function here is how many times is this function called? In instruments, it's called 23 times. In statistical, it's called 16 times. Oh, we run it again? Oh, that time's 20. Another time, that's 10. Our number's not accurate. So we have accuracy versus correctness. And the instrument stuff tells you really precisely what's going on, but because you are injecting code into it, it actually changes the cache and the behavior of it. So we basically call this one right here, instrument stuff has the Heisenberg effect. All right, Heisenberg, if you remember your physics, Heisenberg basically said you cannot measure a particle by observing the particle, you disturb the particle. I'll give you a more proper example. In grade school, when the teacher leaves the room, what happens to the classroom? People are goofing around, playing, right? Teacher walks back to the room, everyone's sitting proper. The way the teacher teaches is one way. When the principal is sitting in the room to observe the teacher and kind of, maybe give feedback or review. Now the teacher behaves differently because the principal's in the room, right? So by observing, it changes your behavior. When I was working in Mexico City, we had TVs blowing up and starting on fire. And when I would come down there, they would see someone from corporate, they would all do the process perfectly. When I leave, they get sloppy. Observing will actually change the behavior, right? So when we do instrumented code, we're adding code in there. We're actually getting a Heisenberg effect. We're observing it, we're changing the flow, we're changing the cache lines a little bit. It goes a little bit slower. So it gives you correct number of functions, but it's not the same behavior because we broke it. All right. When we do this particle stuff, and don't be the first person to do this, for the love of God, just have me keep my job. Do not check in your performance data. I'll show you why in a second. So the first thing you always do with when you do performance, you copy your directory and you do performance there. When you're done, you delete that directory, right? So we go to release, right? And so let's put the particle system up. And make sure the settings are there. I'll show you how this works. All right, so it's 125, 20, right? I actually looked up, these are the colors of the Ukrainian flag. I looked up the RGB.
Oh,
Nice.
All right, so here's the particles running. And this is what I'm going to be grading on, is this little number here in the corner. So right here, I'm just looking at this number here in the corner, and this is, how many milliseconds. Right? So I'm looking at the final number, not the draw and update, just the final number.
and where's the chart for that again? Or would the
Yeah, the chart is how many times faster is how many points you get.
so
You should be getting about 4 times faster.
I mean, my thing is that if you're just seeing our finished code,
I'm gonna run the original code,
then you're right.
that's the time, then run your code and divide
It's
it.
on your machine, yeah, okay, I see.
Right, all right, so now, all right, so here we go. So we got this thing compiling, right? And Make sure I got the directory right. Get out of this. All right, so we'll cut and paste and make a copy. Go in here and all right, so everything going to release. All right, so we made sure it compiles and runs. So now we're going to see what our time is, right? And so first choice is, do we want to be accurate or do we want to be, or do we want to give an accurate representation of time and maybe lose some fidelity on the quality, or do you want high quality, not accurate, right? So those are our choices. So what we're going to do here is this thing runs and builds, right? So cool. We go in here under debug, and it's this profiler performer. Right, so we go into the first one, and it's going to say, here's your choice: computer CPU, right? Oh, or instrumentation. It's in a different location on my computer. All right, so computer CPU. Boom, click the first one. Computer CPU usage. This is the sampler. It's just going to have a timer goes dun 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 dun. Where are you at? Where are you at? Where are you at? So that sampler is happening. And we click this little wagon wheel here. This is how fast we want, right? So we want to go as fast as it allows us. 4,000. Let's see if it goes even higher. Let's do 10,000. Does that allow us? No, that's as fast as it goes. All right, cool. 8,000. So we're gonna get 8,000 samples a second, which actually is kind of slow, but we'll do that. We do this right, and we just hit. You do the target. The target's gonna say, what do you want to run on? Right, the startup target's fine. So then hit start. So it's running full time. So nothing's changed. We're just running it, right? It's collecting data, and I always like to let it go for 2 spins, right? So this thing's running. We'll let it finish 1 whole cycle. There we go. The new cycle starts, and then when this one ends, that's 2 full cycles. And you hit the button, stop collection. Okay, so we just recorded. So it goes sample, 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 8,000 samples a second, and it's recording all those things. And it's going to cook on it, and here's our data, right? What came out of here is, here's all the particles, right? Here's the time it lasted. And it's going to say right here, the particle emitter, sorry that it's small, it says here's draw, it's taken 26% of the time, and the update takes 2.9, so 23 and 27, right? And and then here's the next guy that is the highest function that gets hit is libmsse sign precise, right? Which is the sign function. So out of all the functions in there, these are the top offenders, right? So we can go into this. Here's a little diagram, makes you feel warm and fuzzy, right? So you go into it, you click, here's all the functions. You can see which ones are being called. And this says, hey, this function right here, only 2 times it got hit, right? So we have number of hits and we have how much time we're spending in there, right? So you can see here, here's the draw. The draw is taking 26% of the time, right? It has the most hits. So we can click into that, boom, here's that. And then our code right here shows you, here's the code, and it's like, see, we're spending most of our time right here. We've got 409 hits in this for loop. We hit this function rotate matrix 1,600 times, right? You can kind of see, this is just where the random dice rolled and hit. Now you'll see on this thing, wait a minute, you mean this code didn't get executed, right? There's no hits on it, right? When you're in release mode, it takes all the code and squishes it together And sometimes it removes redundant operations. Sometimes it takes these 3 lines and put it together. So there's not a one-to-one mapping. So this code here is probably buried in these lines above and below it. Yes,
Sorry, I missed a beat. When you, once it says 2 cycles, what button do you hit to get it to actually show you the results?
you just click on it, just start clicking your way through it.
No. When like it's running right now, it's doing 2 spins. How do I hit
There's
stop?
a stop, yeah, stop.
Okay.
Right. So we can look here at the functions and can go deeper in there. We can click in another function and keep going and start seeing which guys are giving us some trouble, right? Like, wow, this one's costing us a lot of cycles, right? But then here in the current view, we can also go in here and go, all right, let's look at the call tree. And this is now, the data is just organized by who calls whom, right? So here's main opens, it calls draw opens, it calls operator delete. We're spending 3% of our time in operator delete. Right? We can go inside here is emitter update. And then inside emitter update, there's particle update, right? And we can go deeper into this and say, oh, look, we're spending all this time in malloc or random or, sine function or cosine function, right? You can start seeing which functions are in there. So this is the call tree. So we have functions call tree. Then we also have this thing called hot path, and hot path says, here's the ones that are kind of burning us right now. They put a little fire, they said, these guys are causing us pain, So this is the sampler, right? And it creates this report. And you can, if you wanted to, you can just sit there and say, I just want to scan the data just between this time frame. So you could put markers in there if you wanted to and say, only look at this amount of it, even though it's recording for 2 minutes, just look at this 5 seconds window of it. And it was selecting the stuff. Again, this tries to figure out what the hot path is, what's causing most trouble. And it will also monitor external code. Visual Studio is running. All these other threads that are running kind of give process in there, right? So this right here is the report that regression, right? And I'm just going to leave it here just to show you what the size is. So here it is, and this is 22 megabytes, not bad, right? Now we're going to do this again. And we're going to go to debug performance. Now we're going to not click this, we're going to click instrument right here. And there's a button here and kind of like you can do more stuff. I just leave this alone. Yeah, cool, thank you. Right. And our program still is again startup, right? So instrument. What this is going to do, this is going to add start and stop to every single function in your whole program. So yes, that's the project I want. Go for it. Yeah, make the right one. Now what's doing is it has to recompile everything. So it recompiles everything. And now it's adding monitoring code into it. It's running right now. So it's running. And we're going through the first one. Now here starts the second one. It's running. Cool. All right, so now it just collected this, but what it did is it print statements, start and stop in every single function. So it's going crazy, and it's going to have to take some time to cook it because there's a lot of data. So it has to just say, hey, start, stop time for this one function. Then they're going to turn around, basically sort it by function, sort it by time, add the time up for all the time you're in that function, how many times it got hit, a lot of little data. So it's going to cook for a little bit. But what this is going to do, it's going to get very accurate, tell you which functions were called, how many times they were called. You run this 3 times in a row, it'll be exact same data 3 times in a row. But you see, it didn't move the same speed, it moved slower. And it's not honoring, because we added all that monitoring code, the caching is a little bit different. Still cooking, we'll see. I think I did that one on recording. We'll see, maybe I crashed the whole system.
Oh, no.
No, okay, it's still cooking.
Got any like stories to tell in the meantime?
Has anybody used a static analyzer in software yet? So basically it walks through your code tree. It's basically like, imagine you have a compiler that is running at warning level 4. It's like warning level 30. It goes through each one and says, if you were a vector, and they follow the whole life of the vector, who touches it, where it touches, what value it could be. It said, potentially, if this thing fails this way and that fails this way, this pointer is not valid. Right, so it's a static analysis. It's really cool. I used one in a real project, video game thing, and this company goes, we got the static analyzer, like your shit won't work, right? Blah blah. And so they gave it to us. It took 7 days of running nonstop, and it crashed.
Oh, my God.
So
Oh,
all right.
no.
All right, so here's this this is the instrumented one, right? It gives you the chart. It's kind of cool. And then we can just click into it, like, okay, update, here it is. And this is what the calling function say, I'm in the update. This update's in the body. And here's new. New is being spent 20% of the time. Execute, or that weird execute that was being complained about, is 19%, right? If I want to look at execute, I click it again, boom, now I'm in execute. The body of the function, oh, I spent all my time in random. So even if you remove that ++ pointer goo and rearrange it, the random function.
So you can't do anything here.
Right, so that's why I looked at execute, when I look at this, I'm like going, it is what it is, that's a constant, I can't change it.
Yeah.
Because remember, if something is taken 1% of the time and you make it 2 times faster, you now went from 1% to 0.5%,
Which is barely anything.
which is like not enough to kind of call home about, right?
Yeah.
So you want to attack things that are big.
So what I've learned from this is don't mess with execute then.
Well, yeah, leave execute. If you learn one thing from this exercise, right?
Oh, new is still 20% too, huh?
Yeah, and that new means not that can you speed up new, it's do you have to call new that many times?
That was actually my question of what you suggested earlier about putting the vector pointers in the particle object, because then you're calling new. If you're taking advantage of the fact that new is aligning the data,
Right, new is a line of data.
right? If you take advantage of that, then every time you,
Yeah, but you're missing the forest from the trees, right?
okay, so.
So the thing to think about, you create all these particle systems, right? And then it finished drawing once and it goes new, draws once, new. Well, let's say you have 125,000 particles,
That's
125,000 news.
Yeah.
Then you get to the bottom, guess what you do?
Yeah.
Delete, 125,000 times, go back to the top, what are you first gonna do? Allocate 125,000. That might be a hit, all right. You can probably remove all those news. You just do it once and keep the particles around, don't throw them away,
Oh, you just update them.
you just recycle them, yeah. All right, so here's the call tree.
Right through.
And the call tree can go deeper into this, but again, you get higher fidelity, you can look into this and see which functions are actually being called. Right.
9 million times to
Yeah.
it was called.
And you can see, I mean, before the sine and cosine were incorrect, and this is exactly the same number now.
Why is delete taking 18% of the time?
The delete, because we're using delete that much. So one of the things you learn in optimization is that most of your time is calling new or delete. So that's why C++ is cool, because you can declare an object on the stack. that makes it a lot faster than calling new, because new is slow, right? Stack is actually a memory allocator. It just moves the pointer down by that size and it's done. Instead of going through that whole linked list and
Yeah.
headers and stuff like that. All right, so anyway, you go deeper into the stuff, you can go as crazy and as deep as you want to go in here. You know, here's all the functions. You can sort by the calls, you can do all the other stuff, but you're gonna see malloc free, these things are gonna be just slammed hard. And then, you know, here's particle update, but inside of there is mostly gonna be the stuff here. So, all right, so this, you know, here you can kind of drill into which functions give you the most help. You know, and kind of see where your code is. So when you highlight in this, it shows you the code that it's hitting. When you call here particle, this is the line that gets hit. So that's your start, right? Start and stop. So this is the function. It doesn't tell you what's happening there. It just says this function was called this many times, right? So let's look at some of the code. So going to the code. You're like, okay, matrix update, right? And you're like, how much is this set giving me trouble, right? So this matrix temp set, right? This is, where was this? This is inside
Particle
update.
Yeah.
So particle.
Oh, guys, update was taking a lot of time.
Particle.
So it didn't,
Here's particle update.
I don't know. Oh yeah, it's upper.
Particle update is down here. And now
3%. Wow.
you see some numbers. Let's see what is.
Street math below.
What?
Nothing, I just saw the comment.
So this is 3% of the time. So this function, this whole function is only taking 3% of the time. Right?
Isn't that?
So now we go into matrix set. Oh, come on. Call tree. All right, so from here we have particle update, right?
That is matrix.
Yeah, I'm not getting anything more.
Matrix inverse is down there, but not.
No.
You can search by name in this, couldn't you? Is it just set?
No, it was too small.
Wouldn't it be called a lot though?
Yeah, but it was only in the 3%. So it got hit by the wrapping function. It wasn't big enough. Right. So anyway, that's this, you know, and this gives you a little bit of stuff, but let me save this. Right. And that file here,
Oh, so we won't even need to run it on ours, you're just gonna give us that?
no, because as your code changes, you're gonna need to change it.
So just keep on.
Building it.
Yeah.
So that file there is 8.2 gigs. So please, please, please do not check this in the Perforce. So copy it, use it, then throw it away, right?
So it wouldn't the percentages effectively stay the same because you're,
Yes, the percentages are the same, but if you need that higher fidelity, you use the instrument,
I guess,
right?
it just is like.
So now, this gives you here, you almost never, like, what was useful here is you kind of go through and like, oh, wow, that random function is so dominant, everything else kind of is useless, I'm not gonna do any more and execute. So boom, that's what you got from this really quickly, right? When you start going deeper in there, you can kind of get like, how long is this one function? Is this function worth optimizing anymore, right?
Yeah.
So the way I optimize is not using this. I use this at the end. When I'm like out of ideas, I use this. There is a program called Visual Studio, Intel VTune, that is like $12,000 for this program, but it will measure bus misses and retries and stuff like that. It's absolutely insane. If you can get it as a student for 3 months, and then when your 3 months ends, you're like, I'm still a student, I still want to use it, and you get another run. You can keep daisy chaining this for a long time. They don't care. If you understand how to read this stuff and use this stuff, the people who do these type of profiling things get about, I don't know if I should tell you the salary, they get good salary, right? They get north of 250,000. Because not many people could do this. And this is kind of the experts where you're like sitting there and looking at stuff. I used to use buses and logic analyzers to do it. And now this stuff simulates it for you. So it's pretty cool. But anyway, you get to see this stuff. It's not as easy as it looks. There's majority of the time you get a trace and then you data mine it, you filter it, you look at things for like a week on that one trace. And you turn around, you do another capture, and you do this in trace. So you get this kind of interesting pattern with optimization profilers. I call it whack-a-mole. You get functions that are hot, right? So like this function is hot, you're like going, I'm gonna work my tail off to make this better. So you lower it, right? But by lowering it, you just disrupted the whole universe. And so then you get another layout. And now suddenly this is super large. Like, wait a minute, how is this possible? Well, you just moved around your cache. And so when you pound out one thing, suddenly the next thing kind of sometimes gets evicted more or does better.
Right.
They're not independent items, they're all interconnected.
Just because something might.
Right, so
seem faster.
so that's what generally happens when you get into the lower level like this, you start tracking stuff this way. So how I profile is a little bit more coarse at first. I have a timer. It's like a stopwatch tick. Timer.
It's all over our.
And then I go timer, talk. And it's gonna measure the time between those locations, between these two. So start the timer, stop the timer, tell me how long it's been, right? And these are coarse, but sometimes a little bit higher level is better. So I'll show you how I do it. Solution here. So here in the main function, I have two timers, update timer and draw timer. And what I'm doing with that is, here's my update tick and then talk, and it gives me my total time. I can go tick and talk, and what I do is I print it out. And so now I can print out my draw time. And what comes out of this is time in seconds. So I just multiply by 1,000 to make it milliseconds, right? So when we do this, let me kick this number smaller. This is
update more than.
So here's the time for the update and time for the draw, right? Then I'm like going, okay, out of the draw, I want to focus on the draw. What's taking the most time on the draw, right? Or let's say the update, you know. So I'm gonna go in here, what's inside this update, right? So I'll just put another timer there. So maybe I'll do this. I'll create a timer here. I'll just make it global, so a quick hack timer, and I'll call it TA, right? And now I put the timer here, and I go into update, which would be the Sparkle. And I'll just sit there, okay, you know, there's a timer called TA, boom, and it lives somewhere else. It lives external to this, right? So there's TA. Then if I want to measure this, I can go, you know what? How long does, you know, how long does this part right here? Let's do TA dot tick. And I like to have this kind of standing out so I can kind of see it, right? So I'm just gonna measure that set, right? And so now what I'm gonna do is just hijack this print statement here and say, you know what? TA. And I'll keep the update and I'll do so that's milliseconds. And then update time, and then here's all right, so let's see what this looks like. You can see it's really small.
Dang.
Right.
So that's not the issue.
So that's, you know, and that's kind of why that program skipped it. It was too small for government work,
I
right?
guess because it's literally just setting a matrix.
Right,
It's not
it's
like
in settings, so it's copy, copy, copy. Then when it gets optimized, it might even be totally there, right?
Yeah.
But once I have this TA, right? I can sit there and say, okay, well, let's give myself like another one, TV. I don't know what I just clicked. Right, and so I just moved these timers around and I started profiling things that I was interested in. So I kind of get gross time and then kind of go from there. Should I keep it run? It's V, not,
Yeah, build really shouldn't be control B. It's very annoying.
yeah,
I do it all the time.
right. Right, so here on my time, I'm just gonna update time. Then TA. I full. Right. Right.
And T and B.
So now I have TA and TB kind of floating around. And now I'll like on, all right, you know, divide and conquer. Which one of these guys is problematic? So I'll put a tick out here. And then maybe I'll put the bottom half here, like TB. And then down here. So kind of like, all right, which two halves are giving me the most trouble, right? So I measure the top half versus the bottom half. So top half versus the bottom half, which part of this function is evil, right? And the catch is, don't assume you understand it, just, test it, right? You can see here, well, this whole function is not really that useful. It's like, I'm in the wrong function. Obviously this is not even interesting because I'm like registering.
Wasn't this function like 12% in the, yeah, wasn't this like pretty big? This is particle update.
Yeah.
Particle update, yeah. Well, we can look at this. It was in particle update or a particle emitter update?
It might have been a emitter update.
Yeah, it might have been emitter update, right? So you can kind of see the drill, right? And
Right.
it is kind of divide and conquer. So this is update, which looks like there's not much going on here. So yeah, so this whole thing, I'm like, that's not really
So
a
the particle
problem
class
thing.
is
So
like-
let's look at emitter. Emitter might be more interesting, right? So now I'll just go over to emitter. Okay, here you go, boom. And now
Emitter update is probably where it's
here's spawn.
update.
Let's put one over spawn. TA that. And then
Yeah, this is definitely gonna be the main one.
right,
This is definitely.
and then here's the update, right? Like, whoa, and then we'll just put this one here.
I mean, wait, yeah, TA is, okay. TA is in the new, right? That's where it was.
Yeah,
Okay, that's gonna,
all right, TB is the winner right now.
why wouldn't TA be? TA is literally creating,
I'm- The data tells him where to go,
Well, creating doesn't take that long.
right?
it's creating millions of nodes.
No, so TA is doing here. TA
If
says,
last, if
it
yours
says
was free.
spawn,
Yeah. so just
and it's calling
spawn.
execute,
Spawn.
right? And then add to particle, so that's all in there. But TB has this spawn, which I think is costly. And it has the update, has removed from particle list, right? Then it has a clear, and then it has push everything back onto a linked list. So this is probably pretty costly.
It takes everything off and then pushes it back on.
I left you some Easter eggs. To attack some easy low hanging fruit that you should be able to fix and win.
Yeah.
So you start to divide and conquer in this stuff. So once you find out where you're at, you're like, okay, this guy's giving me trouble. Now look on your profiler and kind of look more tighter at it. So
Right.
I used a coarse approach and then to the finer approach. Right. So now let's start our lecture.
What?
Yeah.
We ain't even
Yeah,
done.
this is warm up.
Yeah.
All right. Yeah, I went through loops. All right. All right, so this this code here, oh, I forgot one more thing from last week. Did I not push the notes from last week?
I don't think.
No, I must not have.
Mm,
Um,
I was
That's
looking
no
for those and I'm
problem.
like,
Yeah,
where?
yell at me when I do that. It's just an oops on my side. Right, so. Here it is. All right,
Oh, nice.
so this is the particle. We went through all this last week.
Yeah.
Yeah,
Okay, but this is the one I didn't get time because we ran out of time. All right, particle review, right? So you have the particle system, right? And so you need to keep a log, right? So every time you get something working, check it in, but what I would do is just type it into the little description. So you can sit there and check in your code, but where it says change list description, just blob it there. Some students rather just put it into a text file and just keep the text file going, whatever way you want. It's really easy to read the change list later, so do that, it's, very quickly, do this stuff. In industry, it's a good practice because this also kind of is like, this is what I did today, or this is what I've been working on. So when your boss goes, hey, you haven't been working, you're like, there's the logs, right? So here's a couple change lists, samples, right? And what I'm trying to do is to see, I want to see the progress. I want to see your development as you start and you keep getting, what tricks are you doing, what you're missing in that. I can see you kind of walking up to a faster system, right? So, go through this stuff. I'm gonna give you a to-do list of what I did. Yeah,
Mr. Red Hair.
just seeing if you guys read it.
Is that a hint? Is that you throwing a hint at us? That your comments are
Chris
wrong?
Keenan's name out loud.
His comments, is that a hint? Is that what that is?
What is?
Are your comments wrong? Is that a hint?
What comments wrong? Did I cuss my name outside? Yes.
His comments are in the code were wrong.
Oh, yes. Who knows?
Oh, yeah.
Who can say? It's a big thing, right? All right, so some tricks here. Add const everywhere. You can't try to add const until you can't, right? Because const just gives a hint and it goes faster. Whenever you're using a pointer, see if you can get away with a reference. Reference run faster and they're safer and you don't have to worry about it being broke. Remove temporaries, do that plus equals, so you don't create a temporary then add. Right? Look for invariance. If you have something in a for loop and it never changes based off of the index or the count of the loop, remove it out of the loop. So you don't need it. Look for useless work. So this one has some work that's kind of dumb and stupid. It's there to kind of give you something to do this stuff. Dynamic memory timings, right? So what you're gonna do is all your dynamic memory, you gotta ask yourself, if you create 125,000 particles, right? So I call new on this, then somewhere at the end, I call it delete. And the delete might be through the container. I might do STL add, and then literally say STL clear. But then my next loop, I turn around and do the same thing again. Can I reuse those particles so I don't have to call new and delete? As you can see, our new delete is dominant right now. It's costing most of our time. Right. So there's containers. What containers in there right now? What's our STL containers that are being used? That's all vectors. Lists, we're using STL list, right? I've said this before, and I slid this all through the whole quarter. STL, you can write faster than STL, right? You can do your own stuff homemade better than STL. So right now it's using STL list, right? So this is a linked list of items, right? So you have the links to each item, right?
Why do you, wait, so what is printing off there? Hang on.
What?
What's the purpose?
So
of this?
in the code, right?
Yeah, what's
The
actually,
code has a linked list of particles and a linked list on the draw buffer. Right? So there's two linked lists, right?
Right.
So a couple things are to think about. What's faster to walk through? STL. What's faster to walk through? A linked list of 125,000 nodes this way, or an STL vector. Which one's faster if I had to touch every node?
so a vector of 125,000.
Right. Which one's faster
The
The
vector,
linked list.
to touch every node?
Vector takes everything in at once.
Right, so the vector is gonna get a little bit of that. You're gonna get a little bit of that hot cold where you kind of get a couple for free and then it starts reading and then, oh, I'm out of memory, and kind of gets a couple for free. And so you can walk through all of the data
ST
faster in a vector.
So the STL has no limits on the size of the vectors really?
Yeah.
So you can just keep putting,
Right.
just adding probably to the
But-
front, I'd assume.
So right now, we're STL linked lists. They're disjointed, each box is all over the place, so like, shit, not there, reload, shit, not there, reload, right? So this one's gonna be faster, right?
The guarantees there.
But, so now you're like going, okay, you're starting to think like going, this is better, right? So we're gonna just convert STL list to STL vector. That will give you a speed improvement. But now, think about last week's list. How does a vector work? You start off with one, right? You're
Right,
like,
does
oh,
all
I don't need one. Now I have to do two. No, now I have to do three. Remember this?
But this is
No.
the basics, right?
Right, no, this is last week's lecture, STL growth. Remember how when we do pushback? Remember how we did this?
Yeah.
Right, so if you keep doing push back, it's gonna have to keep copying, moving, copying, moving, copying, moving, copying, moving, right? Or you can call reserve. So if you did reserve, we say reserve 125,000 to one allocation,
And then you can just add to
and it just, there's holes in there to fill in. Remember last week's lecture?
it somewhat.
Yeah, all right,
I kind of, yeah, somewhat.
so that gets a little bit better.
I mean, you could also do that hot cold thing where you actually just split it.
Yes, absolutely. Or you can sit there and say, you know what, in my loop, I'm filling up the list and then I'm destroying the list. And I create a new one and I fill it up, right? What if I just sit there and say, oh, it's dirty. Start rewriting the top again. New frame, it's dirty, start rewriting the top.
Couldn't you
So
also,
just keep reusing the same bucket, don't delete it.
couldn't you keep the allegation but delete the data too though?
Why would you delete it later?
Just right
I
over it.
guess.
Just write over it.
I mean, you could also just erase if you really wanted to.
If you need to, you can erase it,
Because
right?
wouldn't there be chance for errors if you just wrote over it?
If you write over every field, it's completely new.
Oh, so you write over it all at once?
Yeah,
Oh,
Because you gotta update all.
so start to think about the memory,
Yeah.
right? So we know a big performance is always news and deletes. And then in this project here, it's using STL lists. Just switching to vector, that's gonna be a huge speed improvement. Doing the vector with reserve, it'd be another speed improvement. Now, don't ever delete the thing.
wait, so would a reserve be at the declaration of
Yeah.
the vector? So you do it like in the header, basically just.
You just say dot reserve
Oh,
in the constructor, yes.
So question, since it seems even more efficient to do a hot cold split
Mhm.
on the walking of the linked list. So in my conception of this, just kind of like thinking through it, let's say I make, because you could also just kind of like allocate an array of particles and then just
Mhm.
leave it,
Yeah,
right?
yeah, that's, I'm getting you like, just because you see code this way. Now, don't get married, don't think that the person who wrote that is a genius. You know, you sit there and like going, wait a minute, you're really doing this. When you look at other people's code, you think a lot of times the code was written with a reason and a purpose. Sometimes it's like, this works,
So.
right? And then as soon as it works, they pat themselves on the back, they think they did a good job.
I get, so my question is like, a lot of tasks kind of like snowball very quickly as you like, there's kind of a ripple effect. It's like, well, if I change this, then this changes this. And so like strategically, how do you like break this up, like parse it into discrete chunks of like, okay, I'm going to sit down today and rewrite this as like an
No,
array
so-
of particles, like.
So let me finish the talk and then we'll give it to strategy, right? So, you know, should you know, is a vector better than STL lists? For our use pattern, yeah, right? You know, what is an STL list good for? A list, a double link list? It's good for deleting one in the middle of a list, right?
You're never
deleting
done.
something in the middle of a array is horrible, because you gotta delete it and squish it all together again, right?
Right.
And if when your list is 125,000, squishing costs a lot of cycles.
Yeah.
Well, maybe what you do is you have it in an array and you go, here's a flag, delete, dirty. Just change the flag to dirty. Just skip that cell.
Oh, it's also interesting because if you make a particle array, arrays of course screw up alignment. And so.
That's why you need that pointer.
What pointer? Oh, yes, and then if you should, well, even then, you need the
But
pointer.
remember, if you declare the pointer trick, you declare it once, you never delete it
Yeah,
Oh, to point it to the
to the vector.
right. So you just offload the news into the particle as opposed to,
You're starting to think this out. There's a lot of different ways to attack this, right?
sure,
So another thing, always overload the big four. If you don't, the compiler can assume to do the most slowest, safest approach. You know, it's not going to be too aggressive on you, right? Time large sections of the code. You know, kind of don't assume you understand what's going on with the code, because the code's going to get compiled, squished together, and rearranged. So put timers in larger sections and say, is this timer faster or slower? Oh, okay, I want to work on this.
so can you go back a slide? So I understand the second bullet point, like, I understand what you mean by that, like in the sense of like, put in some ifs and end ifs to throw in some timers and things like that. And I understand like you kind of do that also with like unit tests, you do an end if kind of Could you like, is there a way we can look up how to do that? Because I understand what you're doing. I
Oh,
understand.
you mean like
conceptually.
how to use if, pound, if, and then.
Yeah, and like how to turn them on and off and all that. 'Cause
Okay,
I-
yeah, no problem. I'll show you that right now. Right here, let me see how many slides I have to go. Here, let me finish this and then we'll go into that. All right,
Like I understand, and if like
no, we'll go off this. Push it on the stack, then later we'll pop your stack.
I just don't want to run past that single.
Right.
I can
All right.
look it up later. I just want to know where to look.
Keep your debug level at warning all. And test it in debug and release. And keep doing that. Just because you work in debug all the time, once in a while, take a step into release, make sure it still works, and go back into debug. If you stay on one island too long and you switch, like, what just broke? Well, I haven't tested release in a week. Now you change so many things. Or if you just did, I did one change, and you just, what I do is my stutter or my, you know how some people will spin their pen around their thumb, you know, when they're like, you know, fidget toy?
Yeah.
When my fidget toy is like, oh, I'll compile and release. Okay, it runs, and go back, I'm like, okay, now what was I gonna do again? And I just do that, I do this so frequently, once in a while I was like, oh, that was kind of cool in the news, what's going on here? And then all of a sudden I release in and out, and then come back. So just make that as a habit. Then this way, what happens is, as you change code, if suddenly it broke, it's probably what you just changed. So you're in the neighborhood of it, right? All right. Logs, right? All right, so that's kind of the general thing here. This which segues into the concept of refactoring, and you hear this term a lot, refactoring. The book was kind of this Martin Fowler was one of the kind of cornerstones in software engineering. He basically kind of formalized this word refactoring, and refactoring is, this is one of those books. And how refactoring works is this book is actually pretty great. It's programming as agnostic. It could be C++, Java, it doesn't matter. The concept of refactoring is still the same. But what you're doing here is you're changing the structure of your code, but you're not changing what it does. So you might have one super function, right? You might then say the smell of that function is it's too large. So break it up into 4 little functions. So one function then calls little functions. That's refactoring. It still does the same work. It just is structured slightly differently. So in the book, they talk about when and why do you refactor? Refactor for maintainability, right? The code is spaghetti. You hacked it together. It's not commented. It's poorly organized, right? So you do it for maintenance reasons. You do it because of architectural support. You want to add a little more structure. You want to add a little more OO functionality. It's a little too loose, a little too wild with pointers. So you start to kind of refactor it for architectural reasons. You also refactor it to get it ready for optimizations. So sometimes this function's too large, I can't really optimize it, but if it was broken into smaller sections, then I can optimize one of those small sections, or I can then one section can be optimized and 4 people can use that one function. Right? All right, so where and when do you do this? You try to do this to make code a little bit easier. All right, so so one of the things here is when you refactor, anytime you touch the code, clean it up. A simple refactoring, right, is really easy. A simple refactoring job is rename the function to what it really does.
Yeah.
Do not take the name there. That's what some author originally came up with. They're like going, it doesn't do that anymore, or it keeps changing and keeps it growing, and also the name makes no sense.
Right.
Smartest thing you do is just name it to what it does, right? That's going to clarify it. They're like, on why is this thing doing a create and over here is doing a create? Hey man, shouldn't the creations be near each other? So you remove things and move things around. When you add a feature, you know, a lot of times refactor it, and then it becomes easier to add that feature. If your class is much more structured and organized, it's much easier to add or extend it, right? But one of the things that you're supposed to do with with refactoring is you test it first, refactor the code, then test it second. So basically, refactoring doesn't change the behavior. It just changes the organization of it. Right? A lot of people don't do this in the wild, but you always had features. So what happens when I come across a bug I wrote in real code, right? I don't fix it. The last thing I do is fix it. You're like, yeah, but you just had a bug. I write a test that crashes or fails. I fix the bug. Now my test passes. What did I just do? I guarantee I never get bit by that bug twice, right? Too often you'll be working with somebody and you're helping them debug and you're going through the code, and you finally going, here it is, here's your problem. It's like, oh yeah, I had that 3 weeks ago. And you just want to strangle the guy because it's like, you spent all this time debugging their problem and they go, oh yeah, this happened 3 weeks ago or a month ago. And it happened again. Or if you add a test to fail, then when you fix it, and you never get bit by the same tiger twice, right? All right. So rule 3, refactor when you add a function, refactor when you fix a bug, or when you're doing a code review, right? So this is kind of the rules on refactoring. But here's what's interesting about this book. The author was going to be a new parent and was freaking out, like, how do I take care of a little kid? I don't know anything. And the mom says, look, they've been raising kids forever, it's you can do it. And so she basically said, if it stinks, change it and make sure you feed the kid at least twice a day, right? So that's like the wisdom from Mama Beck. So he liked that idea, if it stinks, change it. So his whole book is smells. So you go in the cover and go, this function is too large. The smell is too large function. You go flip down to page 33 and it tells you what to do. This function has circular dependency. The smell is circular dependency. You flip down and this is how you break dependency. So basically he has a laundry list of 80 some smells and you just index it to there and it says, this is how you refactor it. So it's really kind of a nice cookbook on how to attack things, right? So here's some of the smells. Duplicate code, divergent, lazy classes, middleman, so basically that's kind of how it works, right? All right, so now let's talk about, you were talking about the pound define or if def?
Yeah, the if that, yeah, it's more like I see you do it when you write our tests, our unit tests, and I visually understand the purpose of pound if and pound end if. And like turning things on and off and blah, 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 but like, I don't know how to implement it.
Yeah, we'll go through
And
it.
You turn them on and off in the IDE especially.
Yeah, it's real, there's an easy way, and there's a more craftier way, right?
As a
So-
follow-up question, can we add classes and files?
Yeah,
Okay, just curious.
yeah, just when you can. Just do not touch or change anything in the OpenGL. Yeah, that's
Except for double and float.
the double float, and I created duplicates there.
Yeah.
Which kind of tells you, I think you should move to a float.
It's quite unsettled.
Yeah, it's very discreet there. All right, so here's a code. All right, what is an if def? That's a good question, because I have been using them a lot, right? So int x x equals 5 x plus equals 6 x plus equals 7, right? All right, so this is, let's make sure this compiles. All right, so here's this code, right? And, oh, I should probably initialize this. What? Oh, and
That's what, yeah.
here we go. All right. So what if I just wanted, I don't want this code, I wanted to do +6 or +7, but I don't want both. I want to say I want to do A or B, right? So I'm gonna say I want to do A or I want to do B, right? Well, what I can do is just put this as conditional code. I can go pound if, right, A. And if pound if B. And if
So this is like an elaborate switch, basically.
it's big, no, it's a compile switch.
Oh,
So right now it's grayed out, right? So then all I do is go pound define A.
I mean, this is what you do in our unit test thing, the unit test configuration. I was just like curious, like how do you actually write yourself?
yeah, I just.
And then if I want this off, now that's one thing. When you see pound if, it says, is this true or false, right? There's another one that's kind of confusing called if defined.
So if it's already been defined somewhere.
This is if it's been defined, period, right? So this has been defined to, to 3, that's on, right? This can be defined to false, right? It's on because it was defined, right? Not defined.
And that's anywhere in the compiled scope. It's not just in that file.
It's so this, no, this right here is scoped here, right?
Yeah, because I've seen you do it like if unit test configuration : A, right? Like something like that, right? Is that,
Well, so that's this. Now you could also, if you wanted to, if you wanted to define, right? Define, if define. You can go here and say solution, right click property. And I'll say preprocessor. And here you can say A. Boom. Now it's part of the program.
Oh.
There.
What? What, but
that's just wrong.
Right,
I think it's very easy
so
to forget.
that's why you almost never, I like having an include that has it defines, because otherwise it's like, where's Waldo, where the hell did it get, like defined, right? So this to me is, I think, kind of borderline uncool to do, right? But you can do that.
yeah, because you're busy trying to find where.
Yeah, you're like, where the hell
I
is it,
mind
right?
finding it.
But remember, you can make this, so if you have a class, right? And you're like going, I want float X and double X, right? You're like, wait a second here. Then you can go. Pound if use, float, right? Pound else. And then
Is there a
Now-
pound else if?
yeah, there's an else if as well.
So
So now if I just define this,
I mean, what is the point of doing this in the compiler? Cause like
what's
what,
there?
cause you're gonna
So
have,
so I could have what this is when you see the pound define and if that's. It's the same as cutting this paste and anything that's grayed out, you delete. And that's your
Right.
file.
well, cause in your cause in your test you flip
Yeah.
it, right, right.
So you can put some timers into your code,
You put
and
timers
then
in your
you,
code.
when you, instead of removing them, just put guards around them and define them out.
as
And
opposed to
then
what
when
we do,
you
which is comment
screw around
one
with
by
some
one.
other
So-
code, you wanna turn them back on.
So, alright, so the timer, here's a trick to use for the timer, right? So I think this is where, let's beat this one up. So here's our code, right? So let's say we wanna time A and time B, we have two different timers, right? We go like this. Timer, let's say A. Right? So like, that's kind of silly, right? What the hell is this, right? Now we take these two. Timer start, right? This will be, TA dot tick. Right? So now, cool, that's really tick and tock, right? But you're like, okay, that didn't say me anything, right? Then we go like this,
Why is it still outlined in red?
what?
It's spelling?
Oh, because I don't have a TA,
Oh, sure.
I'm just kind of giving you this, but then we can go like this. Pound if enable
Timer.
TA, right? Else.
And just make this like equal null or something.
Yeah, do nothing,
Oh, cause then the code still runs, but you just don't.
right? So now.
Huh.
Yeah. So now. This right now does nothing. The code's there, but it's not on. Right?
Well, the timer code's not on. but
The timer's
code
not on,
itself-
right? And then you just go. Pound if, anyways, right, define.
That's 15 minutes.
And now,
Right.
the timer's on. Things like that.
Clever.
Um,
Is there a way to say like if in debug do this if?
Mhm.
Cause I've seen something
yeah,
like that.
so there's, so now you go in here, there's standard ones that use. You have here. A debug, you'll see the word underscore debug.
So you can say if debug,
You can say if underscore debug,
yeah,
right? Then you go not underscore debug is released.
Oh, so it's, oh,
See, and debug,
it's underscore and debug.
right? So you can do this. If I wanted this in debug, right? Say here, let's go with this way. If debug. And this is now pound define. Right, there, it's there.
and if
But
you
now
change
when I
that
go and
to-
release, ready? Right, 1, 2, 3, boop.
Ta-da. Wait,
There we go.
there we go.
Kind of
Yeah.
interesting.
And there's also if and defined, which is if not
Right.
defined, right?
It's right here. We do this, if not defined. It means nobody defined it. Define it. So that means it can only be included once.
Oh,
And then the bottom of that's,
And if, yeah,
oh, so it always runs in this case, because you're always defining it.
no, that's how your headers don't get included multiple times.
right, letters or headers get multiply included.
So even though you
Right.
include it from,
So like, you
Five
could,
different
you could write this,
I see, okay.
Yeah, it prevents all
You-
sorts of
you-
linker
you can
errors,
have
which drives
this,
fucking crazy.
you can. So right here, pound, include, here, you want it to go really down into the rabbit hole, right? So here's A, right? What the hell is happening here, right? It looks simple, right? Here's A is this little class, right? Well, what we do is go here to this, and I'll put it back in debug, sorry. Sure, compiles. Ready for a ride? Here we go. So we go here, do properties. And you want to see code gen. Preprocess, right? Preprocess to file, yes. Okay,
And that does.
right, you'll see.
It'll make a giant file where it has everything
Yeah.
in it all at once.
Right.
Oh,
So now you go to main, you go right click and say compile. Boom. And now it throws everything into
.exe.
this,
Is it main.obj?
no, oh, it's the
Oh,
main that include.
oh, great. No, it was in there, the EXE was in there.
No, it says that. Oh, you bastard, where'd you go?
It was in sandbox, but, or the back one. In that debug. That was where the EXE was. It was the sandbox at EXE, but did it? Because that was saved at 8:59, wasn't it?
It should, oh, sorry. Make sure I had the button right. Run debug, oh, I'm in the wrong one. This is, I can't tell you how many times this happened to me. I switched something here. This says release. No, have it always say active and then you change it only there,
Yeah.
right? So that was my mistake. Pre-process here, there you go, yes. Now, here you go.
What?
No, I'm not running because I went to pre-process land,
Oh, right.
here, compile. All right, so now. Sandbox,
Should be debug. What?
I'll find it, it's somewhere here. Not over. Right, to these shades.
Where the? Saved it on your code. Wait. Assert.h.
I'm so fucked this weekend.
What?
So much to do.
Assert that. Where's it getting that from?
Oh, here I was saying.
Freaking, I still have my other half of my AI.
Oh,
There we go.
it didn't realize what a.h was.
No, because.
That still found.
It's not so bad.
What the? Where's it getting assert.h?
No idea.
Makes no. Did something change
it's
here?
assert that, oh, no, you're in debug, right?
Oh, I clicked the wrong one. Jeez. All right,
Okay, that
it'd be
one.
better if I clicked the right button, right there.
Yeah, that's why you couldn't compile
Like,
zero.
Right, yeah, like what the hell? It did compile, right? Right, compile, boom.
Okay, there we go,
That's
succeeded.
good. So now. There it is, I.
Ta-da.
So this is main, right? Boom. All right, I just want you to look at the line 1.
What the,
line 400,000.
why does that put it all the way?
Here's Maine, so that's when shit gets compiled together. Right? So here it is, and then
It's all
over
the
here,
libraries.
here's your A. Here's your A class,
Is that all just a blank space
and then
between?
these are all literally all the headers from all these other things.
Oh my.
Yeah, this is.
That gets automatically jammed in there,
Right, they talk about it briefly in systems one, like all the parts of this file.
right?
Not in
But now,
our system.
here's the nice thing, when you do that include thing, right? Right,
He's gonna
No,
be,
it's fine, it's absolutely fine, because what's gonna happen.
oh, cause you
is
have the
We have the
thing.
header card, so now when we do compile,
If it's already defined, then I won't be able to define.
right? And now.
Still 407, yeah.
There's the class A, there's no other class A.
Right, cause
Interesting. Make sure I got the new one up here.
That was sincere yawn. It was not a fake yawn, I sincerely.
Yeah, so it was only one A. So that's what really happens when you say include. So this first one goes through and says, hey, I haven't been defined. Says, I haven't been defined, define it, include this shit. The next guy comes in here and goes, all right, here, goes. Hey, has it been defined? Yes, skip it. And it keeps skipping, so we'll only include one. All right, I guess we're done with time, so. You looked a little bit how to use the profiler. I like from the tick and talk, and then when I get lower, then I go into the commercial tool.
yeah,
Start kind of banging that thing out. Tonight I will release PA 9 extra credit and basics 9 extra credit. And then you guys chose the door that I didn't want you to choose. So now I have to write basics 10 for extra credit. So I don't have one done, so I will dream of some kind of evil thing for that.
do you like circles or the
Is there a
geometry
PA
stuff?
10 too?
No.
Just do geometry stuff, just for.
All right, oh, last bit, and I'll shoot this on Piazza. I will have PA 8 has to be due this Saturday, right? And I'm gonna grade it because I want to get it back in your hand because the following Saturday is when I regrade all the PAs.
So you want to,
Need the feedback
yeah,
for PA 8, otherwise you can't redo that. And I'm only regrading PA 1 through 9, I mean 1 through 8, no redoing 9.
One question.
answer 70%, right?
70% maximum. It's not, I don't loft 30% off, I loft. You can't go above 70, so it's actually to your advantage.
Wait, so like, I would still get like a 70.
So like here, let's say you got a, let's say there's 20 points,
Yeah,
right? You get 10,
that's 50. yeah.
that's 50%, but if I lopped off 30%, you would only get 7. Right? I would lop off 30%, so I don't do that way. I just said you
But
can
your
never
maximum-
exceed
yeah.
70%.
So
In
on
the
your
region.
I mean,
see.
it's actually more generous. It's actually more.
I see what it is, okay, okay.
Yeah, because otherwise you get a 30% hit all the time. My mode is, no, you only get a 30% hit if you hit a perfect score.
Oh, okay, that's.
If you like on the PA 4, let's say instead of 20 points, you got 16 points, that's 80%. I will only knock you down to a 14.
If we did,
Right, so like, let's say you redid PA 4, right? It's 20 points, and you only did 10 of them. You would get all 10 points in this scenario.
so like if I had on PA for like RVO, I think I got like 4 at the time.
4 out of
I
10.
get it, what
You-
is the
you-
highest? And I got
4
4 out of 10 for redo.
You get 7. You can't go past
Okay,
7.
that's right, that was my
Yeah,
thought, okay.
I got.
No, I made it in such a way that it only helps you, but you can't like
So you
rate it
had
super high.
a 75 then.
It's-
Then you
You
There's
don't
no
get
point,
some,
if you're above
no
70,
point.
there's no point.
No point.
Okay.
So.
You can redo it to get, you'll get a score, it just, it won't get recorded, that's all.
Right.
Oh shoot.